Welcome everybody to this session. Um, uh, this is a session that will last most of today, ending late at night due to the difficulty of scheduling talks by some of our invited speakers who are on the West Coast. I would like to inform you that the first talk will be at 11:30 because Professor Dodabalapur was not able to join, and Professor Deepak Gupta from IIT Kanpur will be the first speaker.
Okay, okay, sir.
Also, I would like to reiterate what Ritesh has just mentioned in the chat box. Please give him the co-host rights.
हेलो मिस्टर रितेश भारद्वाज।
Yes, yes.
सर एक्चुअली को होस्ट बनाने में एक प्रॉब्लम ये है कि अगर
Excuse me, guys. There might be attendees right now who are listening to you. Please
हेलो
keep this in mind.
हेलो
Yes, yes.
सर एक्चुअली कल भी हमने ना किसी को को होस्ट बनाया था, तो एक्चुअली उन्होंने क्या किया, जब ये मीटिंग लीव करने की जगह ना उन्होंने मीटिंग एंड कर दिया था, तो पूरी मीटिंग एंड हो गई थी।
Okay. In that case, if someone is presenting, then as far as the demo run was concerned, it was told to us that who will be the co-host, that he will be directly transferring or giving the presenter rights to that particular speaker so that he will be able to share the screen. So now,
हाँ
but now you are saying that thing is not there, then how the presenter or speaker will be going to present or share the screen?
सर, आप नीचे अपनी ना स्क्रीन पे एक ऑप्शन देख पा रहे होंगे, शेयर वाला।
Okay.
हाँ, तो वहाँ आप जाके अपने आप बैकग्राउंड में वो आप अपनी स्क्रीन चलाएंगे, फिर इस शेयर बटन पे आके वहां से आप वो अपनी स्क्रीन यहाँ शेयर कर सकते हैं।
That is for me only, na? But as far as
हाँ,
for the speakers, the same thing also will
ये
be there.
सर ये ऑप्शन सबके पास आ रहा होगा अभी।
Excuse me. Can you please do this over chat?
For sure, sir.
Yeah, please do not speak because there are delegates attending right now. Welcome everybody to this symposium. We were not able to conduct the first invited talk at 11 due to some technical difficulties. But we are very pleased to welcome Professor Deepak Gupta from IIT Kanpur, who will be presenting our very first talk. Uh, Professor Deepak Gupta is a professor at Material Science and Engineering, IIT Kanpur, and the co-founder of the Samtel Center for Display Technologies and the National Center for Flexible Electronics at IIT Kanpur, where he was critical in raising funds, architecting, hiring, and operationalizing both centers. He has an active interest in the area of flexible electronics applications in anti-counterfeiting, TFT arrays, and ferroelectric memory arrays. He has more than 10 patents and numerous publications in refereed journals. He has a PhD from UC Berkeley and a BTech in metallurgical engineering from IIT Kanpur. On a personal note, I have known him since 1998 when he taught me my very first classes in material science and engineering. Note for the delegates who are attending this talk, there is an ask question button on your screen that you will need to use to pose any questions at the end of the talk, which I request the speaker to limit to about 25 minutes. I will be able to read some of the questions and allow the speaker to respond to them. All right, so let's get started. Deepak, over to you.
Thank you, Madhu. Thank you for the introduction. Are you able to hear?
Yes, please go ahead.
Okay. So I'm here joined with my, I'm going to present a paper on, this screen gets covered, just one second. Yeah, towards high density non-volatile memory array based on PVDF TRFE ferroelectric polymers. I'm here, my co-authors of paper are right here, and I am this person, and also my co-author Ashutosh is also sitting next to me. In case there are questions, we can jointly take those questions as well. So we've been working on this PVDF TRFE as a ferroelectric and a piezoelectric material for a while, and slowly we are now trying to look at how do we make practical things out of it, especially non-volatile memory in this as a subject of this particular presentation. And as it says towards, that means we're not there. But what I want to show you are the elements that we have developed to make that happen. We are at the Flexible Electronics Center, National Center for Flexible Electronics, which was established in 2014. This is where we do all our work. Just a one slide introduction that the things we do are thin film transistors, which is what the subject of today's presentation will be, organic LEDs, organic photovoltaics, especially on paper, sensors. We make functional inks, copper, silver, gold, screen printable, inkjet printable, etc. Printed batteries. Then use these technologies to make memory and logic, which is where we are heading towards in this presentation. Solar modules. Anti-counterfeiting is another area, big area for us. We also have a startup on anti-counterfeiting. Smart packaging, displays, and healthcare devices. So these are the areas we are interested in. We have a full roll-to-roll line with two printing stations, one right here and one other one right here. And these two printing stations, it has rotary screen printing, inkjet, flexo, gravure, all sorts of things. It has photonic sintering, for photonic sintering. It has UV curing. It has convection, all sorts of drying mechanisms also in there. Plasma treatment. Everything is built into this machine so that one can make nice circuits. So today's talk, this is the way I'll proceed. Motivation, and I'll do an introduction to PVDF, TRFE for those not familiar with the material, and then go through what would be the fabrication steps. How would you proceed to make, once the material is known, then how would you make the devices so that they're scalable, and you can make practical devices out. So as a summary, PVDF TRFE, shown here is of course PVDF, and the copolymer of PVDF and TRFE is known to have very good ferroelectric properties. It has a large spontaneous polarization of 10 microcoulombs per centimeter square. Among the organic materials, that's among the highest. Temperature for processing that is required is low, about 140 degree, 150 degree max, which allows you to make things on plastic. You can make thin films like for a ferroelectric transistor, or thin films or thick films like you would do in a piezoelectric material. Also, this material is biocompatible. That's also really nice. It exists in two forms. One is the alpha phase and a beta phase, as the structure shows that it is the beta phase which is ferroelectric, because you can see the CF2 group, which is the polar group, is giving you a dipole moment all in one direction, and it adds up. Whereas in this geometry, this major components will cancel out, and you'll have only a minor component along the chain. And hence, beta phase is the ferroelectric phase, which is what we need to realize. What you get when you make it is not necessarily beta phase. You have to do some heat treatment and annealing, and then only you are able to realize beta phase. Not only you want beta phase, but you have to have the right microstructure so that all the chains align in the same way. Otherwise, they would have different chains. If they oriented differently, then they would cancel out the polarization. Now, using this, so I'm not going into the material part, which we have done work for last 5-6 years. Today is more about on the application side. So if you look at the piezo side, ferroelectric materials are also piezoelectric, as you know, and pyroelectric. So if you look from that side, then there are several applications envisaged. For example, you sense force and pressure, and you can actually, it's given in this reference, you can go up to 10 kilonewton you can impose over four devices. And we have also made touch sensors out of it. Same thing about strain and bending. You using the piezo coefficient here. You can utilize that application. And here another application is proposed right here, where they're talking about another application proposed where they're talking about gesture recognition through the radiation that is coming out of hand, and that the IR sensor. And because this material is pyroelectric, so that's the property which is being used for sensing that. And similarly, energy harvesting, vibration, acoustic, and vital parameters, picking up on the pulses, etc. You would recognize other than at least 5 of these applications are based on some mechanical or piezo behavior. One of them on the pyro behavior. But that's what we want to. We are exploring the ferroelectric property. So if you and especially towards memory. So if you look at memory, there is a volatile memory like in DRAM and SRAM, and then there are non-volatile memory. This also, our interest is in this FERAM. So that's what we're going to focus on, the FERAM. For those who may not be familiar with devices a lot, but just a brief introduction. If you look at a conventional thin film transistor, TFT, not a MOSFET, but a conventional thin film transistor, then it would look something like this: a source and a drain. For example, ITO. In our case, a semiconductor, which we use as IGZO, indium gallium zinc oxide, an insulator, which is Al2O3, and a gate metal. If you just put together a conventional transistor, what we would get is a characteristic which is shown right here, a IDVG curve, which is shown like there, and it has no hysteresis. It has both are, you can go up and down in voltage, and there's very little hysteresis, as you can see, very minor form shown here, but otherwise it is a thick, necessarily separated line on this scale at least, so it doesn't have much hysteresis. Question is, what would happen if you replace this dielectric Al2O3, by some ferroelectric material? So that's what we want to see. But before we go on to that, let's look at, if you look at DRAM, for example, the typical array of memory. Now, interested in array of memory. It is made in a cell, a simplest cell, which looks something like this, where you have the two grid of, array runs according to these two lines. And these two lines are used to address each cell of the array. One cell is shown here in a very simplistic form. A typical memory cell would actually have multiple capacitors in it. But I'm showing you a simplest, conceptually a simplest cell in which you have a transistor and a dielectric, just a linear dielectric, not a ferroelectric. So clearly, you can use this gate this transistor will charge the dielectric and hold the voltage, but switch off the device, within no time, the dielectric will leak and the memory will be lost. So it's a volatile memory, therefore. However, if you replace the same dielectric transistor by a ferroelectric material, the capacitor, if you replace from a linear dielectric to a ferroelectric, then a ferroelectric, as you know, has a curve, something polarization D or P, much a small difference only, of a small epsilon times E, which is a small number. Then you see a hysteresis loop of this PE curve, and you see a saturation or a remnant polarization, which gives you a polarization up or a polarization down, or down and up, whichever way you want to look at it, doesn't matter. Then it gives you a polarization, remnant polarization, when you remove the field, electric field, which means once this ferroelectric is charged by a voltage in a particular direction, then it will hold its polarization, and therefore you would have written a memory, a non-volatile memory. It will become a non-volatile memory because you would have written an element 1 or 0, depending on what you want to call this. If you want to call this as a Boolean state 1, this as a Boolean state 0, then you would have written 1 or 2, 1 or 0 ferroelectric capacitor, and hence you would have stored the information on the memory. However, this FERAM, which we are talking about, which I showed you in the previous page, also comes in a couple of variants. Is where you can make, this is of course shown as a MOSFET. So this part is a MOSFET here. This part is a MOSFET, but you can imagine an TFT also, if for our interest. But the circuit is something like this. This is the drive line. You can bias this drive line to say 0 and put some voltage on this word line, and also some voltage on the bit line, and based on that you can charge this ferroelectric. You can either polarize it this way or you can polarize it that way. Now what happens is, when you want to read this value, then in that case, for example, you may have to leave example, and there are variety of ways of doing things. You may have to leave this bit line open, floating, and you may have to put a voltage, positive or negative voltage on, and that what it can do, and bias also the word line. Then what would happen is that depending on what the polarization state is, up or down, your bit line voltage, floating voltage, will measure there, and you would get different voltage. From that you will deduce whether it is 0 or 1 state. However, in this process you can also potentially invert the polarization. So after reading, then you have to come back and write it again. That means the readout is destructive. Whereas if you switch to an arrangement where the ferroelectric capacitor is included as the part of the gate dielectric right here, then this problem is avoided, and that's what you're going to focus on. So what we have done is we have made this ferroelectric capacitor, and this capacitor, the PVDF TRFE, its curve is shown. As I said, 10 microcoulomb per centimeter square is the polarization. Nice polarization you can get out of it. Now, if you take a ferroelectric transistor, that means if you replace that Al2O3 by this PVDF TRFE, then clearly, and materials are written right here, you can clearly see that now you start getting in transistor characteristics, you start getting a hysteresis. As you sweep in one direction, then IDVG curve, which was overlapping when the dielectric was linear. Now when you replace it by ferroelectric, because of the polarization state changing from one direction to other direction, now you have a hysteresis loop, and therefore when you remove the bias, so then in that case either you would have been in this state or you've been in this state. So when you want to read it, all you need to do is find what the current is. If current is high, then it is one polarization state, even without biasing the gate. That means without biasing the gate, if you just read what the current between source and drain is for reading out, then if you get a current, then it is one type of polarization state. If you don't get a current, then it is a other kind of polarization state. The readout is non-destructive, and you're not changing the state of the polarization on PVDF TRFE. That's the advantage. So what we have done in now quickly about the characteristics of also this material. piezo and ferroelectric material characteristic both, actually not just the piezo but ferroelectric characteristic also. We have done a variety of things over years from 70th last years, and what we have found is if you do very fast cooling, sample fast cooling, that means if you make PVDF layer and if you anneal it at 140 degrees or so to convert to beta phase and do a very fast cooling, then you get very nice remnant polarization, much higher than if you do the slow cooling. And sample 1 shows slow cooling. This is the perhaps in the air only. Now we have done something more, and we have looked at the composition. If you use the solvents, which is a combination of MEK and DMSO as opposed to just MEK and DMSO, we find that piezoelectric coefficient becomes very high. Very high piezoelectric coefficient we are able to go. In DMSO, we are not able to make films. Though the piezoelectric coefficient may look nice, it is measured only a small ion. But in a continuous film, you need MEK also, and we can, by having a solvent, you can have improvement in piezoelectric property. Simultaneously, if you look at the ferroelectric part of it, then you can see that we have been endurance or the fatigue testing. We have been able to go up to 10 to 5. That's a record result if you use co-solvent, this ratio, and we have patent on this. Then you can have without deterioration the PR holds in a capacitor. In a capacitor form, PR holds, the remnant polarization holds even up to 10 to the power 8 cycles. That's a record result. So we have used this material, and up to here, as I showed, 60 pm per volt was the piezoelectric coefficient. But if you give UV treatment, another one I'm showing, if you give a UV treatment simultaneously to while you are annealing the film, then your piezoelectric coefficient increases even further. So these are the kind of things we have done to improve the material. Now we're going to talk about what the devices are. So we made flexible pressure sensors for using piezo function, and now I'm going to talk about what we have now done on using what we have done to make array of ferroelectric. You have PVDF, TRFE, and one way is that to make a high density memory array, you could actually inkjet print this PVDF TRFE. But the problem arises that it is not easy to jet the PVDF TRFE. Some papers are there, but in order for them to be able to inkjet PVDF TRFE, they have, because of viscosity and surface tension consideration, specific solvents and no specific solvents. Whereas you have seen that depending on what the composition is, what the solvent you use, you can get much better properties, and as a consequence, inkjet printed PVDF TRFE with a limited choice of solvents, etc., you can use, gives a very poor quality film. And inkjet printing, therefore, for device quality is really not feasible. So then that leaves us to more conventional form of thinking, using lithography and annealing and various type of annealing, etc. And towards scalable process, let us try to show you how that can be done for PVDF TRFE. So here is a device where we make source and drain out of ITO on a substrate which could be plastic or glass. On that, Icee is indium gallium zinc oxide is coated. It could be sputter deposited, for example, you get better films, but it can also be done by solution processing. And then you put PVDF TRFE everywhere, and I'll show you step by step everywhere. Question is then how do you open these via holes for making source and drain contact if you do it this way? One may think that why not bring PVDF TRFE below and use source and go and use Icee above PVDF TRFE. Use a gate at the bottom, but why not use bottom gate architecture? The problem with that is if you do PVDF TRFE before Icee, then there's a scope of large it is not possible because there's a sputter damage that can happen. And also when PVDF TRFE gets removed when you do lithography on a pre-existing, if you do lithography on layers where below which is PVDF TRFE. Then after doing lithography, you often need ultrasonification, etc. And during that time, even the PVDF TRFE gets removed. And so this process is also not very resilient if you use a bottom gate architecture. And then we are also looking at how do you get high throughput, because what you're looking at when you make PVDF TRFE layer, you have 1 hour in 140 degrees centigrade. So how through so we'll look at some other things as well. So these are the 2-3 aspects we have looked at in order to make high throughput. One is the annealing and the other is the lithography part, which I will describe first, and then the annealing part. So in next 5 minutes, developing lithography on the PVDF TRFE process. So what we do is we make source and drain, and this is metal, so it's easily patternable. Then we put indium gallium zinc oxide, as I mentioned. That also is simply use semiconductor patterning like method and do that. So that we deposit PVDF TRFE, and now we need to open the via holes. So we open the via holes through lithography, which will be described the next set, and then we do a lift off gate deposition. Yeah. So these are the process steps we follow. Now, if you look at how the question is, once we have deposited the PVDF TRFE, then how do we open the via holes? So we use photoresist protective layer, and then we open, or make the openings in that, and after that we do dry etching, using oxygen plasma. It is possible the selectivity ratio we choose, and we have to be careful in choosing the selectivity ratio, because we ultimately have to remove photoresist also. If you try to remove photoresist by conventional methods, after doing the PVDF TRFE opening, once you open these wires, if you try to remove photoresist, then in that case, even PVDF TRFE will come off, as I had mentioned earlier. So we choose photoresist carefully, which has a selectivity ratio of only 1.5. So what we do is, and the thicknesses appropriately of the two, so that we first do PVDF. First, the PVDF gets, this opening gets made, but simultaneously, the photoresist thickness is so chosen that even photoresist gets removed. By the time this happens, this openings happen, and ultimately, when photoresist is removed, then over etching may happen on this. So if you look at the side wall, what happened? What we have done here is not really made this opening. We have not made the openings here, which is what in a circuit we will have to do for initial experiments. What we have done, we have made openings on a discrete device. We have made it on the pad. So I'm looking at this edge where the opening has been made, and if you look at this, then you find that the side wall thickness is only 10 microns. If it is 10 microns, then if you want to make these openings, then I'll have to allow this 10 microns, about source and drain each would have to be about 30 microns. This has to be about 30 microns, so that you have 10 microns on this side, 10 microns in the center, 10 microns for this side wall, 10 microns for this side wall, and 10 microns in between at least is made available. So I've chosen 30 microns of source and drain. So if you have 30 microns of source and drain, channel length is about 3 micrometer and small overlap. So 30 plus 30 plus 60 plus another 10 microns. So each device would become about 70 microns, and that 70 micron each device represents dots or devices per inch, about 200 not 200 microns, but 250 devices per inch, which is a very good packing density through this process. So then after that, what we do is gate metal, and gate metal, as I said, is done through conventional lift-off process. So and it is possible to do, and this gate metal is this channel in this case, which I'll show you results for, is only 3 microns. So if we look at this, the PVDF TRFE transistor, then the capacitor looks like this. Ferroelectric capacitor is very good, has about a saturation polarization of about 8 or 9 or so, something like this number right here, and it has a decent, and you can see the hysteresis when the transistor is made out of it. The margin that you see is about 10 to power 4. About 10 to power 4 is the margin here for readout. So there's very good margin also available. So clearly we can make good FE for FE-RAM up down to 3 micron channel length. Gate voltage is very low. Programming voltages for a organic ferroelectric is reasonable. Numbers shown here. The building block for therefore for high density memory arrays is possible. High density in context of organic materials rather than. If you look at the retentivity, it's still very low. It's pretty low, retention, 4,000. But this material is prone to that. That's an open question and a challenge. However, this number is as good as what anybody else measures, which is shown right here, which is 10 to the power 3 to 10 to the power 4 order, right here. Now, annealing, for annealing also we've done something. Rather than thermal annealing, to make this process very rapid, we also used optical annealing, giving 100 millisecond dose at an energy flux of 34.4 joules per centimeter square. If by normal thermal annealing, this is the curve we get by the normal thermal annealing process, then in optical annealing also we get a curve which is not as square as we would like it to be let's see whether this can give reasonable transistor or not. If you do that, then with the thermal annealing, as I had shown you earlier also, this is the hysteresis curve, transistor ID VG characteristics. However, when you make, not however, but the optical annealing, also because the capacitor was not as good, you get hysteresis which is not as spread out. Nonetheless, margin which is still available right here, the margin which is available between these two levels is sufficient perhaps to make a memory out of it. So therefore, it is possible to do optical annealing also. With this, I will end. So we have therefore developed the elements of what is required to make a scalable process of PVDF TRFE. Device performance is not compromised except for retention, which is standard everybody is getting, and we have to do something about that also. This is a flexible substrate. So that's where we are heading now. Thank you.
So thank you, Deepak, for a very interesting and a very promising talk regarding this particular technology. And also for keeping to the time limit, because online conferences come with their own severe time constraints that are not reflected in brick and mortar conferences. I would like the audience to pose any questions that they have. So far, I don't have any questions in the chat box, and we'll wait a couple of minutes that we do have, and then we'll proceed. So I have a question, Deepak.
Sure.
So in this particular process, where you're building these devices on flexible substrates, much of the processing that you're doing towards the end is identifiable as conventional silicon-based processing. So for securing the flexible substrate onto a rigid substrate, which I assume is what you did, please correct me if I'm wrong, what was the precise methodology followed?
I'll let Ashutosh answer this question. He's the process expert.
Yeah,
Okay.
hello, hi. Yeah, so basically what we did in this case, it is a substrate. It's a bit thick, as you can see. It's about 125 micron PN substrate. But we are also developing bonding, debonding process, and we are exploring number of things there. One is using laser. So you just do laser exposure from the back side. So first you bond it using an adhesive, and then after doing processing, you can debond the substrate by laser ablation from the back side.
Okay.
Other one, we are also exploring some intermediate adhesives and glues with some selective, let's say, thermal properties, where we can peel it off after applying mild forces at certain temperature after doing all the process. So, but that is work in progress.
So Madhusudan, just quickly expand on this answer a little bit. Is that once you want, at this point of time, we are using a discrete device. So when we make circuits, then yes, it will be a bigger issue. But when you're making a discrete device right now, to develop the process to freestanding works. Second, when you have 3 micron channel length that you're designing, so then conventional processing, you are forced to conventional processing. It is a patterning in metal, so that part is relatively easy. And then because for multiple layers align properly, even on a freestanding surface, we kept the overlap of the next layers even 5 microns. So channel length is still 3 microns, but as I said, device length still is we're keeping 70 microns. So that way you keep enough overlap. So even if so that's a strategy we are adopting apart from the laser system which is getting built for the
Right.
bonding.
Okay, thank you.
Okay, thank you.
So at this time, I would like to welcome Professor Pasuraman Swaminathan from IIT Madras, who will be our next speaker. Dr. Pasuraman is an associate professor in the Department of Metallurgical and Materials Engineering at IIT Madras and is head of the Electronics, Materials and Thin Films Lab. He graduated from IITM with a BTech and an MTech dual degree. He completed his PhD from University of Illinois, a postdoctoral fellowship from Johns Hopkins, and he worked at Intel Corporation as a yield engineer before joining IITM in 2013. He conducts online courses on NPTEL Swayam platform and has published a textbook published by Wiley on semiconductor materials. He was awarded the Young Faculty Recognition Award in 2018 by IITM for excellence in teaching and research. His group works in the area of chemically synthesized thin films and printed electronic devices. Once again, I would like to request him to limit the talk to about 25 minutes and also request all delegates to use the ask question control on their screens to pose any questions. So over to you, Pasuraman.
Yeah, thank you very much, Professor. Can you hear me?
Yes, we can hear you. Please proceed.
Okay, perfect. Yeah, thank you very much. Good afternoon, everyone. So thank you for this opportunity to present my work here as part of ICEE. My first ICEE conference was in 2018 in Bangalore. And it's a really nice forum to actually meet with people who are working in related areas. So thanks to the organizers for doing this online and making all the arrangements. Today I'm going to tell you a bit about the work that we do in our group on transparent touch sensors. So before I start, I must acknowledge the students and the group members who actually do all the work. In this talk, I'll be focusing on the work of two of my PhD students, Nitish and Sarvari. So Nitish has been primarily working on synthesizing the ink and also fabricating the touch sensors. And Sarvari has also been working on encapsulation and ink preparation. There are also two project associates involved. Shidin has been working primarily on the electronics part, making touch panels, while Arju has also been working on ink synthesis. So Nitish will be having a poster in this afternoon where he'll talk a bit about the capacitance of these touch sensors, basically using COMSOL. And one of my other students, Bhargavi, also has a poster this afternoon, and she'll be talking about wearable heaters, again based out of silver nanowires. For the last couple of years, we have been working on transparent electrodes, and primarily for flexible applications. And while there are a variety of materials, we have been focused on silver nanowires. Silver because we know that it is a metal, so it has very good electrical conductivity. At the same time, when we have nanowires, due to the high aspect ratio, primarily the length to the diameter ratio, we can get very good transparency. More importantly, for flexible devices, silver nanowires show very good retention of their resistance. So if you look at the change in resistance to the original resistance as a function of the bending cycles, in the case of silver nanowires, we see almost a negligible change in resistance compared to other conventionally used TCOs like say ITO or FTO. Silver nanowires are highly suitable when it comes to making flexible transparent conductors. So in order to, sorry, go ahead. Yeah. So in order to actually fabricate these devices, we have a direct write system. This is actually a custom built system which which we made in collaboration with a company called Swasta Manufacturing. This is actually a startup that has come out of IIT Madras Center for Innovation. So this is an extrusion-based writer system where the dispersion can be nanowires or nanoparticles in some solvent, is extruded from a syringe, and the extrusion is controlled by whatever pattern that we feed in from the computer. We also have a substrate bed and a syringe which moves in mutually perpendicular directions, so we can print the desired pattern. In order to make printable inks, especially with silver nanowires, the most important thing that we need to control is the length, simply because if we have too long wires, then they will tend to clog the printer nozzle, so you can no longer extrude out the ink. So we have been doing experiments where we reduce the length of the nanowires by using ultrasonication. And for the nozzles that we use, these are 200 micrometers in diameter. We find that typically lengths of 40 micrometers or less are extrudable and printable. We also control the viscosity of the ink by adding ethylene glycol, and this also helps in controlling the surface tension. So we'll start by looking at the optoelectronic properties of these patterns. So we print very simple square patterns on a PET substrate, and we can build the thickness of these layers by printing more than one pass. So one pass is just one layer of the pattern. 2 and 3 just means we're building more and more on top of it. As we increase the thickness of the material, I'll go ahead. As we increase the thickness of the material, the sheet resistance drops. Again, this is because we have more silver nanowires, but at the same time, the transmittance is also reduced because we have more scattering. So essentially, we need to sort of arrive at an optimum value of both sheet resistance and transmittance, which in turn depends upon the application that we are using these materials. Moving on from pure silver nanowires, we've also been working on making composite ink by mixing or blending silver nanowires with different materials. So in this particular example, we mix silver nanowires with P.PSS. P.PSS is a transparent conductor that's normally used in organic electronics, and we made a printable composite ink. So the composite ink has similar optoelectronic properties to silver nanowires. We get low sheet resistance. At the same time, we have good transmittance. But more importantly, the composite ink has better stability. It has both better mechanical stability and also thermal stability. We can measure mechanical stability, and by that I primarily mean the adhesion with the substrate by using a very simple Scotch tape test. So in this case, we have pure silver nanowires. We also have the nanowire composite. We deposit this on the PET substrate, and then we just apply a Scotch tape, and then we peel it off. In the case of pure silver nanowires, the wires are removed by the Scotch tape, but this is not true in the case of the nanocomposite. We can repeat the same thing on glass, and we see a similar behavior where the nanocomposite shows much superior adhesion. In order to quantify this, we can look at the change in resistance as a function of the number of peel-offs, and we find that for a 4-pass, so essentially when we have 4 layers, even after doing the Scotch tape test close to 9 times, the change in resistance is more or less negligible. For a single pass pattern, the change in resistance is around 70%, but it is still not too bad when we compare it to pure silver nanowires, which are removed by even a single pass of the peel-off test. The nanocomposite also has very good thermal stability. So when we heat silver nanowires at around 300 degrees C, the wires tend to degrade, and mostly we are left with is completely lost. On the other hand, the nanocomposite, when it's heated, shape. Of course, for most flexible substrates, 300 is a really high thermal budget. For example, if you're dealing with PET substrates, typically the thermal budget is around 150 degrees centigrade. So far it's about both the ink and also depositing it to form a film. So now I'll move on to the touch sensor part. When we think about touch sensors, one class of sensors are primarily resistive sensors. So these consist of two conducting pieces, which are usually separated by an insulating spacer layer. So when we touch, so either with a finger or with a stylus, we apply a local force and a local pressure, and this causes a resistance change, and the resistance change can be measured. Another way by which we can implement touch sensors is by measuring capacitance change. So in this case, your finger can either act as one of the electrodes, or we can also have a projected where the finger or the stylus modifies the electric field between two electrodes, and this modified electric field is then detected as a touch. Both of these we can then build in the form of a touch panel, which consists of a series of touch sensors in the form of an. In our group, we have been mostly working on the capacitive touch sensors. And when we think about capacitive sensors, so again, we can have an out-of-plane structure. The most common example, of course, is a parallel plate capacitor, where we have two electrodes which are separated by a dielectric. So the capacitance is inversely proportional to the distance between the two electrodes. So again, when we touch, the pressure that we apply will cause a change in the value of D, which can then cause a change in capacitance, which we can detect. We can make this out-of-plane structure touch sensor to a touch panel by using a series of electrodes which are separated by a dielectric, and I'll talk a bit about this later. When it comes to printed electronics, it's actually easier to implement an in-plane structure where we have two interdigitated electrodes and we can then encapsulate them in a dielectric. The advantage of this approach is that we can print all of the electrodes in one pass or two pass, primarily because we have the structure with us. And when it comes to transparency, because there are less number of layers here, scattering here is lower, which means the transparency of this structure would be better than the out-of-plane structure. So here I show the various steps that are involved in printing an in-plane sensor. So we start off with a PET sheet. We then print the electrode pattern. In this particular case, we have used the pure silver nanowire ink, but we can do the same with the composite ink. This is then dried at 100 degrees C for an hour. We then use PDMS as a transparent dielectric and an encapsulation layer. And PDMS also cures at relatively low temperatures, so we are well within the thermal budget of the PET sheet. So this is a picture of the fabricated sensor. So we have actually 4 electrodes here, and we make individual electrical connections to them. And whenever we touch, we find that there is a capacitive change, and this capacitive change can be measured. Now, because this is printed on a PET sheet, which is flexible, and our silver nanowires are also flexible, we have checked it's working in both the normal condition and the bend condition, and there is no change. The sensor works well. And because we are individually connecting the electrodes, these work in both single touch and multi-touch. So in this particular example, we have 4 electrodes. So we can think of this as a 2x2 matrix. And then the idea is to sort of build this up and make larger matrix type transparent sensors. To further understand how the touch sensor works, we try to calculate the capacitance of these sensors. So Nitish will be talking about this in greater detail in the poster session in the afternoon. So if you look at the top view of the sensor, we have the interdigitated electrode. And this is a side view showing the nanowire, the PET, and the PDMS. So the total capacitance is the sum of three of these terms, C1, C2, and C3. C2 is similar to your parallel plate capacitor term. It is going to depend on the thickness of the silver nanowires. And this thickness term is much smaller when compared to PET and PDMS. The C2 term is small. Mostly the contribution comes from the capacitance C1 through the PET sheet and C3 through the PDM. We have used COMSOL to model the capacitance of this interdigitated design. These are the parameters that we use. We take the material parameters that are directly available in the COMSOL library. We also wanted to look at what will happen when we touch, or what is the change in capacitance on touch. In order to do that, we model the finger as a highly absorbing layer with a large value of epsilon r. The finger is grounded. More importantly, for the initial simulation, we do not consider any applied force. So we do not consider any effect of deformation of the sensor because of touch. But we also did a separate experiment where we just looked at the effect of bending on the capacitance value. So these are some of the results in brief. So if you looked at the electric field, most of the electric field tends to be concentrated in between the electrodes. So this is the top view and this is the side view. Well, there is also some out of plane field. However, when we bring in the finger, because this is a highly absorbing layer, we find that the value of the value of the field here is greatly reduced. We can look at the capacitance both with and without touch, and we find that the simulated values are more or less matching with the experimental data. We also looked at the capacitance change with bending. So if you look at a structure here, you can bend along the AA axis or along the BB prime axis. And in both of these cases, we can bend at different radii. And using that, we can calculate the change in capacitance. So bending along this axis seems to have a greater effect than along the BB prime axis. But more importantly, the changes are small enough such that the sensitivity of the device does not change much, whether it works in the normal state or on the bend state. One of the advantages of using something like COMSOL is that it allows us to interrogate a variety of different sensor designs, which means from this we can actually choose the design that we want to implement for our particular application. So moving on, we now like to talk about how we take this and try to fabricate a touch panel. So when we think of a touch panel, we have a series of electrodes. So in this particular case, we have M and N connections. So we have a total number of M plus N connections. This allows us to access M cross N touch points, and these touch points are primarily found at the intersection of these electrodes. We can also have a different design, which is a diamond design, which again works on a similar basis. So there have been groups that have been working on making inkjet printed transparent touch panels. So this was work that was published earlier this year by Gao et al., where they looked at this kind of a design, and they used an ionic ink in order to fabricate the touch panels. They then used an Arduino board and a capacitive digital converter chip, a CDC chip, in order to interface with a USB. Using this, they were able to show both single touch and multi-touch by measuring the change in the capacitance at the individual touch point. They were also able to show that the sensor works whether it is in the normal state or whether they apply some sort of a strain to the material. So we started working on a touch panel implementation, and this is work that we have been doing in collaboration with Saint-Gobain, and they actually have a research division in the IITM Research Park. So this is a collaborative work with them. Unfortunately, when we started this work was when the pandemic hit, and we were sort of forced to close our labs. and everyone had to disperse. So in order to implement the electronics, what we did was I talked with my project associate and asked him to implement sort of a do-it-yourself touch panel using just simple copper conductive tapes which are separated by a layer of paper. So the paper forms the dielectric. So these are the copper tapes. We then asked them to stick it on a cardboard and then encapsulate it with sellotape. The main idea was to, since we could not fabricate a transparent touch sensor, we will use this as the touch sensor and then work on the electronics part so that we can implement the touch panel. So we started off with MPR121 chip, which is primarily a proximity capacitive sensor. And then we used an Arduino Mega in order to interface with both a touchscreen display and also with a USB. So this is an example of a 4x4 panel, which means we have 4 connections here, 4 connections here, a total of 8, which allows us to access a total of 16 touch points. So we implemented a very simple calculator program where we programmed each of these points to have one particular value. And then by just using Arduino Mega, we can then show that this works as a calculator. We can also implement multiple touch. So in this case, this is a 6x6 array, which means we have a total of 36 points. And then we can, when we touch, we can measure the capacitive change at the points where we touch, and this capacitive change can then be used for some other added functionality. We've also been able to implement both a swipe and a pinch. So swipe we implement by considering a timed touch of multiple points, say along a row or a column. So based on how fast or how soon we touch the next point, we consider these multiple touch to be a swipe. We can also do this and then implement a pinch, which means on the same touch panel, we can implement various functionalities. So this is actually a video, but given the fact that you're trying to stream this online, I will not run the video, but the link to the video is below. And if you want to have more details, you are always free to contact me my email. But using this touch panel, we were able to show single, multi-touch, swipe, and pinch functionality, all using the same panel. So one of the issues with using NPR121 is that there is a tendency to have a ghost touch, because whenever we touch a particular point, the capacitance in both the row and the column tend to get affected, which means we might end up with some ghost points which we actually didn't want. So in order to overcome this difficulty, we shifted from MPR121 to AD7746 CDC kind of IC. And this is work that we are in progress to try and again implement all of the various functionalities using this module. So with this, I'll just summarize. So we have been working on integrating the transparent touch panel with the control electronics. And of course, from the material side, we can optimize the touch panel both in terms of the conductivity and in terms of the transparency. So with Saint-Gobain, we are actually interested in printing these transparent touch panels on flexible electrochromic displays. So the idea is we can then control the displays by whatever is printed on top. And then these displays can be then integrated in, say, an automotive window in order to make smart windows, or there can be other applications as well. One of the things we are also working on is to actually quantify the touch. So question is, can we measure the pressure that we apply at a particular point, which means what is now a touch sensor will then become a tactile sensor. And this is a project that we are doing as part of the MHRD STARS program. So with this, I'll stop. I would like to thank our collaborators, so Saint-Gobain and also STARS MHRD for the funding, and I'll be happy to answer your questions. Thank you.
Thank you, Parasuraman, for a very interesting talk on touch sensors. So I would like to open up the floor to any questions that the audience may have. I would request the conference host to relay any such questions from the delegate side to me as quickly as possible. So while we await questions, I have a very brief question.
Sure,
Are
yeah.
you guys planning to go for fingerprint recognition or any such applications where that seems to be a logical extension to this work?
Yeah, thank you. That's actually a very interesting question. So that's something that we are interested in. So maybe once we have implemented the electronics, we'll think about it. Again, I'm primarily come from a materials background, so the electronics implementation is something that I'm learning right now. But yeah, we are looking at different applications.
Okay, thank you.
Yeah. So I did get a question about any other solvent other than ethylene glycol. So we have used both ethylene glycol and water and a mixture, and we find that that's the one that allows the nanowires to be separate and not agglomerate. We also tried ethanol, but in ethanol the wires just tended to clump together and uh, they were no longer dispersed. So ethylene glycol and water is what we have found to work so far. So we didn't explore any other solvents too much.
Just a quick question out of curiosity. In your solvent mix, what was the surface tension that you observed? Did you measure the surface tension of that mix?
Yeah, we did measure the surface tension of the mix. We know that normally for printed application, we need surface tension greater than 40 Newton per meter, 40 millinewton per meter. I don't remember the exact value right now. I think it was closer to 60, but I'll have to look it up.
Normally, aqua sinks suffer from that problem because the surface tension is too high. So I was wondering how much you were able to moderate that using ethylene glycol.
So at least for the nano composite, we know that we have around 33% ethylene glycol. The rest is water. So I think using that we were able to reduce the surface tension. But as I said, I don't remember the exact number right now.
No, of course not. Yeah. Playing with water in printing is always a bit of a challenge.
Yeah.
So let us thank our speaker again for a very interesting and informative talk, and for having the patience to answer our questions. So now we will move on to the next talk in the program, which happens to be the first oral presentation. This will be presented by Dr. Ratul Kumar Barua from Tezpur University, and the title of the presentation is Modeling of Delamination and Interfacial Stress in a Printed Flexible Electronic Device. I request the speaker to limit the talk to 12 minutes and no longer. That will permit us to entertain any questions for the remaining 3 minutes of the allotted time. Please proceed. Ratul, you can start. Please share your screen and get started. You may want to unmute yourself. Can't hear you. Ratul, please unmute yourself.
Good
Yeah.
afternoon, everyone. So this is our presentation. The name is Sintering and Delamination in a Printed Flexible Electronic Device. So as we all know that printed electronics are making huge strides nowadays. It was first introduced around 1903 by a person named Albert Hansen, who secured a patent for it. And after that, people have looked into it for over a century, and nowadays it's almost everywhere. Printed devices in your cell phones, and the PCB is basically printed circuit board, so it's basically everywhere. A subset of the printed electronics are the flexible printed electronics, and you can see in this graph that it is almost a $1 billion market, printed flexible electronics. So we are going to work on this subtopic of the printed electronics devices. But first, let's see how the traditional flexible electronics devices are manufactured. Usually, they have a lot of manufacturing steps such as photolithography, spin coating, transfer printing, and most of them are usually sputtered or manufactured in a EV evaporator. And they have all the traditional CMOS manufacturing steps like the reactive ion etching and etc. So all these manufacturing techniques are time consuming and costly, which also limits the usability and the throughput of the devices. So the solution of achieving faster throughput and higher yield, low cost, is the printed electronics devices. So basically, the flexible electronics can be now printed using the printed. So that's the concept. So first, let us look into the steps of printed electronics manufacturing. It basically consists of 3 steps. First of all is the synthesis of the ink. So we need the ink to print on some paper or some substrate. So the ink is consists of mostly nanoparticles. Gold, copper, and silver are the most commonly used ones. So once they are fabricated, the silver ones, they can be fabricated in a solution. They are usually coated with a stabilizing agent. So the purpose of the stabilizing agent is it has a dual purpose. One is to prevent the nanoparticle from coalescing together and also prevent them from oxidizing. Suppose a nanoparticle like zinc is very reactive. So if it comes in contact with the outer atmosphere, it will promptly form zinc oxide. And zinc oxide is not a very good nanoparticle for printed electronics because the melting point of zinc oxide is relatively higher than zinc. So PVP or polyvinyl pyrrolidone is one of the stabilizing agents which is commonly used as the stabilizing agent. So once you have formed the ink, then we can print it. So one of the most useful and the mostly used technique is the inkjet printing here, and also the inkjet printing and the aerosol printing device. Aerosol print. So although inkjet printing is the most used one, it has some limitations because it can only allow low density inks. The viscosity of the inks used in inkjet printing are around 8 to 12 centipoise, which seriously limits its applicability to newly developed inks or for applications which require higher viscosity inks. Also, this technique suffers from poor directionality and hence poor resolution, which limits the application in high performance devices. This one is the aerosol printing device, and it can tolerate a much higher range of ink viscosity, up to about 2000 centipoise compared to inkjet printing. In aerosol printing, the nanoparticles are deposited in epitaxial style, and then when the nanoparticles are deposited, they need to be sintered to obtain a conductive pattern. So you may be familiar with the Gibbs-Thomson relation, which says that when a particle is very small, the melting points becomes lower. So what happens is that so gold, usually the melting point is around 1300 to 1400 Kelvin, but when it is very small, the melting point can be substantially lower. So using these three steps, we'll see how can the flexible electronics devices can be printed. So now the reliability studies of the flexible electronics devices is of huge interest to both industry and academia. So to conform properly, the devices need to bend together to hand or some surfaces so that they can read out So here you see a study by Elzobi et al., where he studied all the bending diameters, bending frequency, and bending radius, and figured out a combination which affects the delamination in the substrate. Now below you see there is another study where it was shown that damage increases during high strain. They show that the device lifetime, the device here is a copper film on a PI substrate, polyimide substrate. It can be improved dramatically by coating it with 10 nanometer and 100 nanometer aluminum capping.
Sorry for interrupting, Rahul. Can you please get to your study quickly? Because if we keep looking at the background, we won't get there.
Yes. So this study by Zhang et al. Forces it studies the major forces which are responsible for crack propagation in a flexible device containing the oxide and organic layers. They point out two failure mechanisms, namely oxide layer cracking and oxide organic layer delamination, which co-evolve, ultimately leading to the device failure. All these studies are very good, but they mostly are done on the devices which are transfer printed or manufactured using the traditional devices. So in our study, we are going to do the devices which are printed by aerosol printing. So now I just have said that the melting point of the gold is around 1400 Kelvin, but it can be suppressed to about 1200 to about 600 when the nanoparticle diameter is very small. But you may know that the substrates on which the devices are printed, they have a glass transition temperature of about 200 degrees centigrade. So if you need 600 Kelvin or about 325 degrees centigrade, that substrate will break. So we did a molecular dynamics simulation using a LAMP software. Here the nanoparticle was a single crystalline nanoparticle with the FCC lattice having a diameter of 3 nanometer. And then we ramped up the temperature of the system from 300 Kelvin to about I show here the result up to 1400 using a Nusshofer thermostat to observe the melting process. Here we see that even though the melting temperature is about 700 degrees centigrade, partial melting starts occurring around 200 degrees centigrade. So 200 degrees centigrade for sintering, we don't need full melting, even partial melting. Even in this state, the middle state, it's good enough for a device to sinter and become conductive. So here, this is the device. This is aerosol printed, and we have considered the gold nanoparticles on a polyimide substrate. So we have done some abacus simulation to show that a device, when it is bent, so the top part of the device will have the highest stress. This device was done using a 20 micrometer gold and a 125 micrometer layer of polyimide. For simulating the temperature distribution, a pulse of 2 milliseconds with the energy of 20 joule per centimeter square was used. Now, why 2 milliseconds? I will come in the next slide. So as I have said, that we have printed this, we can print this device by aerosol printing technique. Now, after aerosol printing, to render them conductive, one of the techniques that is used is known as the photonic sintering. So what we do is we have a plastic substrate, and then we put it under a xenon lamp. So, and the xenon lamp is turned on for 2 milliseconds, and that should be enough to sinter the nanoparticles together. The reason is the xenon lamp works by the concept that the nanoparticles are predominantly black and they can absorb all the heat. So this simulation shows that this simulation is done when a xenon lamp has been illuminated at an energy of 20 joule per centimeter square, and the peak temperature was achieved around 1 millisecond. But you see the highest temperature is not achieved at is achieved around 2 milliseconds because the temperature needs some time to spread out here. Now, so it says that there is a temperature difference between the top substrate and the bottom substrate, and this change in temperature will lead to some interfacial stress. And if the time of the illumination and the energy is not optimized, it can cause delamination. So now, we can deposit like a thick nanoparticle layer on top, and when we subject it to sintering, the top part will be conductive, but the bottom part can contain unsintered nanoparticles. So this particular structure can be modeled as two layers, where the first layer is affected by a force, and the second layer, they are connected by this unsintered nanoparticle layer in between. So what happens is that we can do some COMSOL simulation to figure out the interfacial stress between the nanoparticles, and using this formula we can calculate the interfacial stress. So at different temperature, the difference in the delta T is the temperature difference between the conductive layer and the substrate. And if the interfacial stress between the nanoparticle and the substrate is higher than the adhesion force of the nanoparticle and the substrate, there will be delamination. So this is the second cause of delamination, the first of which was bending. The third cause of delamination can be the crack formation, which happens due to drying. So the aerosol printing process contains some liquid. One could be the butylene and methanol, which assist for the deposition process. And when this is deposited, the sample needs to be dried. And during drying, it is a known fact that some crack appears. Here I show a SEM image of the sample. Now, if there are cracks inherent in the substrate, when we bend the substrate repeatedly, these micro cracks will grow, and this can cause some and this can cause some delamination. So Here I conclude my talk. So we are trying to investigate the sintering mechanism and delamination in a printed flexible device. And using molecular dynamics simulation, we show that the partial melting occurs around 200, which is much less than the glass transition temperature, making it possible for sintering to occur in a flexible substrate. So now for a few of the most common types of delamination is bending, then stress during sintering, and also one of the cause which I have not shown, I have skipped the slide, is about peeling. So the peeling occurs when we apply a substrate in a human body and we want to peel off from a sacrificial layer. So if the addition force between the sacrificial layer and the substrate is high enough, this can also cause delamination. So yeah, this is my talk, and if there is any question.
So thank you, Ratul. We'll have time for just one quick question because you only 1 minute left on the clock. I'm requesting the delegates to pose questions using the Ask Question link on their screen. If there are no questions, we would like to thank the speaker again for a very good talk, and we would like to move to the next speaker. This is Ms. Indu Bala from Icee Mohali, who is supposed to speak on liquid crystalline materials in organic optoelectronics. I don't think she has joined yet, so let us wait for the period of time that is allotted to her. It does not seem likely that the person is actually joining, and so lunch break starts at 1 o'clock. So this session is, I guess, can be considered as reflectively over. We will be starting at, let me take a look at the schedule. We'll be starting at 2 o'clock because the invited lecture 4, that was by Professor Bakar Mezari of IIT Kanpur, is cancelled because of some health issue that Professor Mazhari communicated a couple of days ago. So we will meet at 2 o'clock, same place, and I'll see you at that time. Please enjoy your lunch. I'm sorry we can't meet over lunch, as is customary in a brick and mortar conference. So the first speaker is Yogita Methani. She comes from IIT Delhi, and her title of her presentation is a highly flexible and conductive silver nanorod embedded PDMS electrode. Yogita, please get started. You've got 12 minutes, at the end of which we will have 3 minutes of questions. Please unmute yourself. Yogita, please
Hello.
unmute yourself. Yeah,
Yes, sir. I am
we can hear
audible.
you. Yes, you are. Please proceed.
Sir, my screen is visible or not?
Yes, it is visible. Please proceed.
Hello, everyone. I am Yogita Methani, working as a research scholar at Physics Department, IIT Delhi. I will be presenting here our work on a highly flexible and conducting silver nanorods embedded PDMS electrode. The outline of this presentation will be like this: introduction, motivation, experimental methods, result and discussion, conclusion, followed by references and acknowledgement. In this work, we propose a fabrication method of stretchable conducting electrode. In this work, we propose a fabrication method of stretchable conducting electrode using silver nanorods embedded in polydimethyl siloxane, which is also called PDMS. Sorry. Then we investigated its mechanical properties and electrical properties. Sir, am I audible?
Yes, you're audible. Please proceed.
Yes. Generally, there are two main strategies for fabrication of flexible conducting electrode. First one is by coating of metal on top of flexible substrate using different deposition techniques. Second one is using conducting material as a filler such as carbon black metal nanowires and carbon nanotube and mixing these fillers into the polymer matrix. The main challenge is for this is uniform mixing of filler in the matrix. Then PDMS is used as the flexible substrate due to its chemical inert nature, biocompatible natures, but due to its low surface energy and hydrophobic nature, a metal film cannot stick on it easily, which limits its mechanical durability while using as a conductive electrode. The deposited film can crack and peel off from the PDMS substrate. So here we propose a different method to make it conductive, and nanoindentation is used to study its mechanical properties at local scale. Now coming to the experimental method, the silver nanorods were grown over silicon substrate shown in image D and E using lancing angle deposition technique. In this slide, first image is showing our GLAD instrument. GLAD is a different type of physical vapor deposition in which we keep our substrate on a tilt angle with the incident vapor flux as shown in image B. The material can be evaporated by thermal or E-beam source at high vacuum. It offers the wide range of nanostructures by controlling parameters like substrate rotation and deposition rate. Here we fabricated two types of sample. First, normal PDMS film and second, silver nanorods embedded PDMS film. For this, the PDMS mixture was spin coated on silicon vapor at 500 rpm and cured for 30 minutes at 80 degrees centigrade, then peeled off from the substrate. In this way, for second substrate, we seen silver nanorods were fully embedded in surface layer of PDMS with a thin surface region of silver PDMS composite with a much thicker layer of excess PDMS on the bottom, as shown in the figure. All the characterization and measurements were conducted on the upper surface of the sample. Figure C is showing the optical image of a peeling process for silver nanorods embedded PDMS film. Coming to the characterization, this is the same image of grown silver nanorods. We saw that it has a diameter of 150 nanometer and length about 1 micrometer. The chemical EDX analysis confirmed the presence of silver as a primary component. The peaks in the XRD pattern shows the polycrystalline nature of silver nanorods. This slide shows the SAM and AFM images of both samples. Figure A shows the uniformity of PDMS film, while in figure B, a silver nanorods PDMS film shows the permeation of PDMS into the voids present in the porous silver nanorods structures. The surface of PDMS film was relatively flat and smooth, having low surface roughness as compared to the silver nanorods PDMS. For the measurement, we use nano indentation for mechanical study. The indentation was performed by ultra nano hardness tester using Berkowitz diamond indenter. In this experiment, load is applied to the sample by indenter and its corresponding penetration depth is measured. Then by analyzing this force penetration data, the mechanical properties such as elastic modulus and hardness of materials were calculated using these formulas. This the elastic modulus and hardness of both the sample were obtained by the quasi-static nano-indentation method in force control mode. The loads are varied from 30 micronewton to 200 micronewton as shown in the figure A. The figure A is showing force penetration depth curve for both the sample. Figure B is AFM images for the indent created by the indentation experiment. Figure B is showing the indent for 50 micronewton loads and figure C is showing the indent for 200 micronewton loads using Berkowitz tip. These indents were the images is for the silver nanorods embedded PDMS film. These indents have a similar triangular shape as same as the cross section of three-sided Berkowitz tip. The shape and size of the indents increased with an increasing load as the second indent is larger in size. These are the results of quasi-static indentation. Figure A is showing relations in penetration depth and applied force. The penetration depth increases with the applied load and is always less for silver nanorods PDMS film than for the PDMS film. The elastic modulus and hardness decreases with the applied force as shown in figure B and C. Results show an enhancement of modulus and hardness for the silver nanorods PDMS film compared to the bare PDMS. And now coming for the second experiment, there is another mode for indentation in which we can measure elastic modulus and hardness of material as a function of penetration depth. It is called dynamic indentation. It is also called sinus mode indentation. In this mode, during the force loading, the force signal is superimposed by the small amplitude of oscillations as shown in the figure A, the first part of the graph. It continuously measures the mechanical properties such as elastic modulus and hardness during the penetration. Figure B is showing force penetration depth curve here for the PDMS and silver nanorods embedded PDMS samples. Here we applied 500 micronewton peak loads with the frequency 10 Hz for the whole time. As shown in the figure A, the horizontal line is showing the whole time for the whole time of 10 seconds. So these are the results for sinus mode indentation. The modulus and hardness as a function of penetration depth for PDMS and silver nanorods PDMS are shown in the figures. Both samples show the decrease in elastic modulus and hardness values with the penetration depth due to the indentation depth effect, which has a similar trend as for the quasi-static indentation. This shows an enhancement of modulus and hardness for the silver nanorods embedded PDMS as compared to the film. This can be due to the reinforcement effect of silver nanorods on the PDMS matrix. AG nanorods act as a high surface area nanofillers and impose restriction against the molecular motion of PDMS chains due to the absorption of polymer chain on the surface of nanorods. The mechanism of improvement can be explained as the positive effect of high aspect ratio of silver nanorods, reinforcement, and strong, and can be due to the strong interfacial adhesion of silver nanorods in the PDMS matrix. This slide shows the electrical. This slide shows the conducting behavior of fabricated electrode. AG nanorods were uniformly distributed in the entire electrode area of PDMS surface, with one end on the surface and other fully embedded into the PDMS matrix. This implies that the silver nanorods show long-range ordered connection, indicating that interconnected networks of silver nanorods serve as a pathway for electrical conduction. The stability of electrical conductivity under the various mechanical strain of fabricated silver nanorods PDMS film was qualitatively demonstrated using LED circuit as shown in the figure E. The film performance under different mechanical variations such as bending and twisting is shown in the figure B and C. Figure D is showing the IV characteristic of fabricated sample, which is showing its conducting behavior. This slide shows the electrical stability of silver nanorods embedded PDMS electrode with the yes, sir. With different mechanical stretching. The original length of the electrode was 10 mm as shown in the figure. With the stepwise stretching, it is stretched up to 19 mm. It shows that the LED illumination is maintained under stretching condition up to 90% strain. In addition, this shows that the AG nanorods embedded PDMS electrode has excellent durability without losing its electrical conduction, and it retained its electrical conductivity for 10 test cycle. These results show the potential of silver nanorods PDMS electrode in flexible electronic circuit for stretchable device application. With this, I will like to conclude my presentation. We have discussed that we have grown the silver nanorods using glancing angle deposition system. Then we embedded it in PDMS matrix. Then we did its mechanical and electrical characterization and showed that it become highly electrical conductive with an improvement in mechanical property. These are the references used in our work. Recently, this work has been published in Journal of Applied Polymer Science. I would like to thank JATC DRDO IIT Delhi for this project support, and Nanoscale Research Facility IIT Delhi for the characterization facility. With this, I would like to conclude my presentation. Thank you very much.
Thank you, Yogita. Now we'll open the floor to questions. We have only 1 minute left on the clock, so we can have one question or two short questions.
Yes, sir.
Let me see if there's anything in the chat. I don't see anything in the chat yet.
Yes, sir.
I'll ask a quick question. What is the ultimate application for this electrode? Where are you going to use it?
Sir, we are going to use it for some kind of biosensor to measure some electrical activity from our body, means human body. We are planning out it for the next work.
Okay, all right, thank you.
Yes, sir. Thank you, sir.
Yogita, you may mute yourself and unshare your screen.
Okay. Thank you, sir.
Yeah, thanks. So the next talk is by Ms. Suman Mandal of IIT Kharagpur. The title of her presentation is Low Power Consuming High Performance Flexible Organic Field Effect Transistor for Humidity Sensing Applications. Suman, please share your screen and start it as soon as possible. Once again, to delegates, yes, go ahead, please.
Okay, just a minute. So
I'm sorry,
my slide
you were listed
is
as Miss. Actually.
Okay.
Yes, it is visible.
So
I'm actually looking at the summary slide.
okay.
All right. So you have 12 minutes for the talk, and after that we'll have questions. Thank you. Please get
Uh,
started.
okay, I'm Suman Mondol. Okay, today I'm presenting my work on low power consuming, high performance, flexible organic field effect transistors for humidity sensing applications. So this is the so let's start with the overview of the organic electronics. So there is several application nowadays in organic electronics. That's all of we know that. So it's one make a work in photovoltaics, light emitting diodes or transistors. And nowadays these are the real application you can see here from the organic electronics are already available. Some of them are already available in the market also. And here we basically focus on the transistor parts because we are work on the transistor parts. Now, in offits, here you can see offits consist of several layers basically. It starts from the substrate, then need to deposit the gate, dielectric materials, and organic semiconductor, then source and drain, and that is the schematic of the one transistors offits basically. And if you want to use the offit as a sensor, then either the dielectric materials or the semiconducting materials, or both of them can be used as a together can be used as a sensing layer to sense some stimuli. Now here what we did, we basically want to use the dielectric layer as a sensing layer. Now why we choose the dielectric layer? Because due to the gate field. So when we bias the gate, there is a huge electric field we generated in the gate dielectrics. Now what it did when we apply the gate field, then it basically part of the sensing signal, and it's basically what so it's basically a part of the sensing signals, and it improve the sensitivity of the device and signal to noise ratio. Now the thing is that if we want to use it use it as a sensor for real life applications, then what we need some requirements. And what we need basically low operating voltage of the device. It should be highly sensitive, it should have some fast response property, it should be lightweight, and it should be suitable for wearable applications. Now, keep in mind all the requirements. We basically fabricate the device, and you can see this is our flexible device. This is the schematic of our device, and here we basically use the gelatin as a sensing materials of humidity sensing material. Basically we want to use as a humidity sensors, and pentacene as a semiconducting layer. Now optimizing all the device basically parameters parameters, we fabricated the base device, and we have found that the device highest mobility of the device is around 0.33 centimeter square per volt second. And the operating voltage of the device, you can see from here, it's 2 volt, and that means that the device basically suitable for or flexible and portable applications also. Now, as we fabricate already the base devices, then we want to use it as a sensor. Now, when we want to use it as a sensor, we need to characterize the device in different conditions. That means we want to use as a humidity sensor. So that's why we need to measure the sensing property at different relative humidity condition. And here you can see the transfer characteristics of the device at different relative humidity conditions. So it starts from relative humidity condition from 10% to 80%. And when we change the relative humidity condition from 10% to 80%, we get a huge change in device currents. So you can see from here, so 10 to 13,000, almost 1,000 times of improvement of current. So that means that we can use this device as a good humidity sensors. But interestingly, what we have found another things that with the off current also, with increment of the relative humidity condition, the off current basically also increases. And then again, we basically want to investigate on that. And we found that the leakage current also there shows the same type of behavior. It's basically because due to the gelatin. So when gelatin absorbs the water molecules, it basically generates some protons, and that protons basically contribute as a current in the device. So that's why when we increase the relative humidity condition, then basically the current in the here also in leakage current also increases. But when we we increase the gate voltage, then at a certain then leakage current basically decreases, and at a certain voltage the direction of the current basically changes, and we define that voltage as a corrosive voltage. Now, here we can see that the device can basically work at 0 volt also, because at 0 volt we get some a huge amount of current. It's around 1000 nanoamps. So that means that we can use it as a cell bias sensor or energy harvesting device. Now, as we use this sensor as a humidity sensor, so that means that we need to calibrate some parameter of the device with relative humidity conditions. So that's why we check all the parameters of the transistors and vary with the relative humidity condition, and we have found that most of them are basically shows the nonlinear property. So that means that these parameters are not suitable for calibration curves. Then we go to the sensitivity of the device also, because it is also another parameter. And here we found an interesting thing, that it shows basically the voltage, electric field dependency. That means that when we apply when the gate voltage is 0 volt, then it shows it, that means it is just a two terminal device, and then it shows basically an exponential nature in the sensitivity. You can see from here in the G, and then when we increase the gate voltage step by step, that at -2 volt you can see when it is the gate voltage is -2 volt, then interestingly the nature of the sensitivity curve is changes from exponential nature to the linear nature. So that means we can use this parameter to calibrate the device. Then to check if the immediate application of this sensor, what we have done, we basically use this sensor as a cell bias humidity monitoring system, so that can measure the breathing profile of human beings. And here you can see the response of the humidity response from breathing profiles. Yes. At cell bias condition means that VGS and VDS is equal to 0 volt. Now another things I want to discuss here, it is really important nowadays. It's basically the mobility overestimation in the organic field effect transistors. So nowadays it is quite known that the mobility overestimations mainly comes from three main causes. So which is basically double slope in the transfer characteristics, high contact resistance, and the gate voltage dependent contact resistance. Now, here from this figure, you can see in a transfer characteristics. So, if you have double slope and you consider the higher slope and you calculate the mobility, then it's basically overestimated your device mobility. Because so actually in this paper what they shows that if you consider the higher mobility and calculate it and model the device, and then you can see here it's basically the output characteristics of the device is not measured, not basically matches with the measure and calculated value when we consider in the higher mobility, means the higher slope of the device. But when we choose the lower slope, then it's basically matches. So that means that if we consider the higher slope of the transfer characteristics and calculated the mobility, then it's overestimated your device. And another things is important thing is basically reviewed by Liu et al. That is that basically it arises mainly due to the mismatch of the Fermi levels, which basically arises the contact resistance. Now, if the contact resistance increases, then the double slope arises in the transfer characteristics of the devices. Now, another important thing is that which basically means in the literature is the capacitance effect in the transistors. So that capacitance effects can also basically overestimate the mobility. So when we use the polar and ionic dielectric layer in offsets. Now to check this, so what we have done, we first cross check all the things like the contact resistance of the device, and then we check the gate voltage dependent contact resistance. So we have found that contact resistance of the device is very low, and it is independent of the gate voltage. Then we check the transfer characteristics of the device. Here you can see our device don't show any double slope. So it is a single slope. So that means that type of error we don't get. Uh, But the thing is that here we have used gelatin as a dielectric layer. That means that gelatin has some polar groups like NH2 and COOH, and it also has some ions. So because it's absorbed the water molecules and generates some protons inside it, so that means that it has some polar groups and ionic contribution in the dielectric materials. So the thing is that another thing is that when we measure the dielectric transfer characteristics of the device, we measure it in DC bias condition. Now when we calculate the this mobility of the device using these equations, saturation mobility, this is saturation mobility, then we use the capacitance of the device. Now when we measure the capacitance, we measure this capacitance in AC bias conditions. So that means we need some frequency. Now the question arises that at which frequency then we should measure the capacitance and use this capacitance to calculate the mobility of the device. Now, here we can guess that as we measure the device and DC bias conditions, so we should measure the capacitance of the device at lower frequency range. But at which frequency range we basically lower frequency means that at which frequency range we need to measure that things I need to know, because otherwise it will overestimate the device mobility. You can see from this table that if we consider the capacitance at frequency 20 millihertz, then the mobility of the device you can calculate it's around 0.33. But if we consider the capacitance at 100 kilohertz, that means that you get the mobility at 4.1 centimeters per pole second. That is basically overestimated mobility, because at that frequency range the polar and ionic components are inactive when you measure the capacitance. But in your transfer characteristics, as you measure it in DC conditions, so these are active. So that's why you need to measure it low frequency range, but you need to know that at which frequency range. Means low frequency means at which frequency range you need to go. So that's why what we have done, we have need to know the polarization time, and we have performed the bias trace effect. So it shows the anomalous bias trace effect because it has some polar groups. And from that the anomalous bias trace effect, we have calculated the polarization time. And that polarization time give an idea about the frequency, corresponding frequency. So at which frequency we need to measure the capacitance of the device to basically measure the mobility of the mobility of our device. Here you can see the capacitance and the mobility of the device at different frequency. So here if we measure the capacitance at higher frequency and calculate the mobility at considering this frequency range, considering the capacitance at that frequency range, then it's basically overestimated of the device, the mobility. Now going to the summary. So we basically fabricated the high performance low power consuming offsets, which is basically flexible in nature, and we have used it as a humidity sensor that work in the range between 10% to 80% relative humidity condition at room temperature. Then and again we saw that it is a very good types of humidity sensor. It's a 1,000 times of current change observed during the
One
relative
minute.
humidity constant change when we change it 10 to 80%, and it shows an higher sensitivity and fast response. And then again we discuss the mobility of our estimation in terms of frequency dependent capacitance. Now acknowledgements and thank you. Thank
Thank
you.
you so much. This was a very nice talk, especially the level of care you have shown towards the mobility extraction
Yes,
in organic or disordered TFTs, which is actually
yes,
has been
really
a scandal for a very long time in literature. So I would like to open the floor for questions. We can, given the time permitted, allow one or two questions at most at this time.
So I have some questions. Okay. Fluid structure of the constant. This. So I check the chat, and in chat we get one question. Can I answer this question?
Yeah, please do, please do, please do.
So we basically use here the PET as a flexible materials, but you can use another flexible materials also like pen. Pen is suitable because pen can sustain also higher temperatures compared to the PET. And you can also use the Kapton. Kapton can use for higher temperature compared to the PEN also. So you can use in general PET, PEN, Kaptons, like this type of flexible materials.
Okay,
And
so
nowadays people are also working on the stretchable objects, so they use the PDMS also as a substrate material.
okay, so thanks, Suman, once again for a very nice talk.
Thank
And
you.
now it's time to actually move on to the next speaker,
Okay, thank
which
you.
is Mr. Jibin Samuel from IIC Bangalore, who will be talking about diketoparylopyrrole based polymers for N-type organic electrochemical transistors.
Thank you,
Jibin,
sir.
please.
Yeah, thank you. I'll be sharing my screen.
So yes, please go ahead. Please limit yourself to 12 minutes approximately, because we'll need time for questions.
Sure. Okay. Hello, everyone. My name is Jibin. I work with Dr. Nagafani Iktukuri in the Solid State and Structural Chemistry Unit, Indian Institute of Science, Bangalore. So I'll be talking about my work on diketopyrrolopyrrole based polymers for N-type organic electrochemical transistors. To understand what OECTs or organic electrochemical transistors are, let us compare it with a device which we are more familiar with, the organic thin film transistor. So in the thin film transistor, we have a source and a drain contact, um, which is bridged by a semiconducting channel. So when you apply gate voltage, we apply gate voltage through the dielectric, and the dielectric polarizes, and we induce charge carriers at the interface, at the gate dielectric, at the channel dielectric interface. So the charges are induced electrostatically. But if you compare that with an OECT, the charges are induced in a different way, in that the charges are induced due to an electrochemical reaction in the channel. So the gate voltage is, the channel is in direct contact with an electrolyte. An example would be like sodium chloride solution, and the gate voltage is applied through the electrolyte. To understand this further, how an OICT really works, we'll just focus on the channel electrolyte interface. So I was saying the channel is in direct contact with the electrolyte. So when a gate voltage is applied, the channel is in its neutral state, and it has a very high resistance. So when you apply a gate voltage, the ions migrate towards the opposite interfaces based on the voltage that you apply. And in this case, I'm considering a N-type transistor, and you need a positive voltage for it to turn on. So when the gate voltage exceeds threshold voltage here, which I give by E is equal to E reduction, so that corresponds to the reduction potential, the electrochemical reduction potential of the polymer material. The polymer undergoes an electrochemical reduction, as I've shown in the equation. The polymer takes on one electron, so the polymer becomes a polymer minus. So an electron is induced on the polymer, which delocalizes on the polymer backbone. And to counter that charge, a cation from the electrolyte moves into the polymer. So the ions move into the bulk of the polymer. So basically, the conductivity of the channel is modulated by the oxidation state, change of the oxidation state of the channel. So now the question to ask is, why do we need OECTs, and what is so special about these devices? Okay, some of the key features of OECTs are, one, it is the low voltage operation. So here I have compared with the same material that I'm using for my OECTs, an earlier reported work from our group, which is a thin film transistor, an FET, field effect transistor. And on the right, I am showing an OECT characteristics that I'm talking about. So we see that a magnitude threshold voltage, it's in the few tens of volts. As you're familiar with OFETs, there's a few tens of volts. But in the case of an OECT, we have the threshold voltage is less than a volt. So immediately it brings up, now you have sub-threshold operation, sub 1 volt threshold voltages, which makes operation in active electrolytes possible. Okay, and the second feature, I spoke about how the field effect transistors work. The field effect in the field effect devices, the carriers are induced close to in a 2D layer close to the gate channel interface. However, if we compare an OECT, the carriers are induced through the bulk of the polymer channel. That means there is three-dimensional doping, which implies that the change in conductivity occurs not only at the interface but through the bulk, which gives because doping is three-dimensional, a small change in the gate voltage would imply a large change in the channel conductance because you have the entire channel turning on and off. Okay, this translates to a high transconductance, which means these devices could be very sensitive sensors. Okay, another feature. So I spoke about the electrolyte being in direct contact with the channel material. Now this opens up the possibility of functionalizing the channel material itself so that material like, if say we want to sense an analyte and it's in the solution, it could diffuse straight into the channel and diffuse through the bulk of the channel, making the channel very sensitive. It could, the analyte could diffuse in through the channel and modulate the conductivity, thereby making it a very good candidate for sensors. Now we put the three key features together: low voltage operation, high sensitivity, and the possibility of transport of analyte into the channel, not just on the interface. You increase the total sensing surface area. This makes OECTs an ideal biosensor element. So is that all, or are there more possibilities? That's the question that I want to ask. No, it doesn't stop there. We can go on to think of OECT-based circuits, which we can integrate into these sensors. So as we increase the complexity of sensors, may say we are making a sensor array. So it becomes important to integrate signal processing, multiplexing, and control circuits. So all this is possible if we make OECT-based circuits. So what are the challenges? So when we think of sensors, one important thing is maintaining a low power consumption, and the immediate thing that comes to our mind is a CMOS type implementation. But a CMOS type implementation requires that we have N and P type materials, right? They have N and P type materials which have similar performance. But the state of the art for OECTs is that there are very few N type materials that are available. In fact, there are only 2 reported materials so far. And even the best N-type OECT material that has been reported is at least 5 times less as good as the P-type OECT material. So in terms of material, discovering new materials, there is a challenge for OECTs. So that is where we come in, and we propose this new material, which has been explored in FET, in FETs, and this is a diketopyrrolopyrrole based polymer, where there is this, it's a diketopyrrolopyrrole conjugated with a thiophene group. And these materials have traditionally shown very high N-type charge carrier mobilities in FET geometries. So this is a very good N-type FET material, but now we are looking at how we can use them as OECT materials. So going on, I will talk about how we fabricated the OECTs. The OECTs fabricated in a simple three-step process. First, we pattern gold electrical contacts using photolithography. Then we deposit the insulator layer, and it defines the active surface area. And the third step is spin coating the semiconducting polymer solution to make a thin film. And this is a schematic of the final device. So I have shown a chip. In the middle of the chip are the devices. So all the devices are shown. The device, the channel width is about 40 micron to put in perspective. So this is the microscopic image of the devices that were fabricated. Going on, how did we measure these OECTs? So we can, as I've shown here, there's the OECT chip on which we paste the polypropylene well, in which we pour the electrolyte, and we have a silver wire coil dipping in, which makes it the gate electrode. So we have a full OECT setup ready for measurement. So now, like any transistor, the first thing that we want to do is try and see like how these work. Are they turning on and off? So the first thing that we did is we did a transfer characteristic measurement where we hold the drain bias constant and sweep the gate voltage and measure the drain current. So we see as a typical transistor, we see as the gate voltage increases, there is a threshold voltage beyond which the drain current increases. Drain current increases. So we have a clear off and on state, and we have a transistor that works as an N-type OECT in an aqueous electrolyte. So we reached our goal, and now we want to compare it with materials that have been reported earlier. So earlier I had spoken about 2 materials that have been reported earlier. So I've listed, one way of comparing the performance of an OECT is to look at its figure of merit calculation, which is the product of its mobility and the capacitance. The capacitance here is a volumetric capacitance because I was talking about volumetric doping. So the volumetric capacitance is given by the formula here, where GM max is the maximum transconductance of the device, and W, D, and L are the transistor dimensions, and VT is the threshold. So we see that our device is at least 2 times better than the best material that has been reported so far. So that makes our work special in that there are few materials, and we have added the possibility of looking at these class of materials as OECD materials. So with that, I would also like now go ahead with the traditional measurements that we do with any transistor, which is the output characteristics. Here also it shows a typical transistor behavior where you have a linear region. As you increase the drain current, as you increase the drain bias, the drain current increases linearly and then saturates, the typical transistor behavior. And we also have the switching characteristics. So we have the on and off, the device goes on and off as we switch the gate pulses. So with that, we have demonstrated N-type OECTs with material that are still not yet been looked at in OECTs. And we have shown that these are stable devices. We can show stable transient output characteristics. Also, preliminary results indicate a performance that is better than the reported OECT materials. With that, I want to acknowledge SENSE, the NNFC, National Nanofabrication Facility in SENSE, and the Department of Instrumentation and Applied Physics, and MNCF at SENSE for the facilities that they offered. With that, I would like to thank you, and I would like to questions.
Thank you, Jibin, and especially for keeping to the time schedule I had requested.
Sure.
I would like to open up the floor to questions from the audience. Please post your questions using the Ask Question link in the control from the delegate screen. I would like to open up that question session with a simple question of my own.
Yes.
This lack of good N-type materials in polymers and organics in general has been a long-standing issue. As a chemist, can you comment on why that is the case, and what are the strategies that are possible to design our way out of this problem?
Okay. Okay. So I'll pull my screen back on. So one challenge with N-type materials is that the stability of the material in ambient. So that's an important problem. So N-type materials tend to have they tend to lose electrons. So you dope the channel and they lose electrons to reaction to oxygen and to water. So that is the main challenge with N-type material. So how the challenge is overcome in this material. So that's why DPP, the diketopyrrolopyrrole group, is very important. That these diketopyrrolopyrrole groups have the LUMO levels. So the LUMO level is where you put, when you dope, you put the electron in. That's the lowest unoccupied molecular orbital. And the LUMO level is in the stability window, within the electrochemical stability window of water. So what DPP does, what is special about DPP is that they are very electronegative. And they tend to be very electron deficient, and they tend to pull the LUMO level down. So wherever you put a DPP in a polymer, that's what the DPP does for the polymer. So that's my take on what is the challenge and how it can be overcome.
If electronegativity is the key to this solution, then why not use some fluorinated groups?
Some? Sorry? Fluorinated groups. Okay. So that's something that people have been trying, but that's not the only thing in field effect transistors. If you think about, if you're talking about transistors, an important thing is not only the stability, but also the mobility of the carriers. So for mobility, you need good backbone planarity, and also you need the chains to pack very well, so that not only do you have good transport on the polymer backbone, but as well good transport between the polymer backbones. So you need intramolecular and intermolecular transport, and you need the right groups to be there. So the functionalization, all these bulky groups that you see are to ensure that the polymer has the right crystalline structure and you get very good mobilities. So the design is very important. Yeah.
So please take a look at your chat box and see if there are any questions that might be pending.
Right now. Okay, so some Ajish has asked me if if I have done any diffusion modeling. No, I have not done any modeling on these devices. So yeah.
Okay. So with that, let us thank the speaker again for a very nice talk, and also particularly to keeping to the program. The next talk is again from IISc Bangalore, and this will be presented by Ms. Monalisha. The title Title of a presentation is Magnetic and Transport Properties of Semiconducting Cobalt Ferrite Thin Films for Flexible Spintronics. Limit yourself again to 12 minutes because we'll need time for the questions.
Okay. Am I audible? Hello?
Yes, please proceed.
Okay. Good afternoon. So I'm Monalisha. Today I'm going to talk about electrical and magnetic properties of semiconducting flexible cobalt ferrite thin film. So the content is, first I will introduce what is the real reason of studying this flexible magnetic semiconductor. Then I will talk about the characterization of this sample, and I will give a conclusion. Okay. So we know that cobalt ferrite is a well-known ferrimagnetic material with a hard magnetic behavior. It has very nice magnetic properties. But the problem is it is highly insulating in nature. So that restricts for real-life applications. So in our case, I'm working on neuromorphic computing. And for the application in neuromorphic computing, we want it to be either semiconducting or conducting. So just in one line, in neuromorphic computing, we try to mimic the brain. We make computers which will mimic brain features. So we try to realize it. We try to make this insulating cobalt ferrite into a semiconductor. So we try to dope with ruthenium 4+. Why ruthenium 4+? Because by doping with this, the magnetic and structural properties won't change. However, it will turn a insulator to one semiconductor. So why we want to do it? Because we want to use this material as a channel for a synaptic transistor. So this is the final transistor we made. So so basically, again also we try to add flexibility, because as I told that we're trying to mimic a brain, and all the devices we work are 2D, but we want interconnected 3D devices. So if it has flexibility, then we can bend it and we can achieve interconnectivity compared to our brain. So I won't talk about this device, but I will just restrict my talk to how we did a ruthenium doping to cobalt ferrite thin film, and we retained the magnetic and structural properties. However, we changed the electrical property, and also how we added flexibility. Yeah. So we have used mica substrate. Mica is a flexible substrate. We have grown CRFO thin film using PLD, and we saw that. Just 1 minute. We saw that it has all the films are in NLL oriented. It has a pretextual nature, and it has very a small value of FWHM, showing a very good quality. Again, it is deposited on mica substrate, which is transparent and flexible. So it is adding flexibility to our device. Then we see that the thin film has a very small roughness of 0.2. On the top of that, when we did a UV visible spectroscopy measurement, we saw that it is also visible in the visible. It is transparent in the visible region. And adding to that, with ruthenium doping, there is not much change, because this line is corresponding to cobalt ferrite. However, this is corresponding to ruthenium doped cobalt ferrite. So then coming to we did Raman measurement to see whether there is any structural change in the sample with ruthenium doping, and we saw that this is for cobalt ferrite. This is for after doping with ruthenium, and we saw that there is not much change in the peak values, also compared to the bulk value, which is showing that there is no structural change with ruthenium doping. So till now, we saw that there is no change in structural property with ruthenium doping. Then coming to magnetic properties, we check that by doing in-plane and out-of-plane magnetic measurement at room temperature, we saw that cobalt ferrite is isotropic, and comparing to doped and undoped sample, we saw that with doping, the magnetic properties doesn't change much. However, there is a slight reduction, but the properties remains intact. Then to check the flexibility, we did the magnetic measurement with bending. This is what the sample, undoped sample. This is for doped sample. We did MH measurement at room temperature, and we checked that, and we applied bending in a 2 mm bending radius. We applied tensile and compressive strain, and we saw that there is no change in magnetic properties with applying bending in both doped and undoped sample. So this shows that there is not much change in magnetic property with ruthenium doping and also with bending. So till now we realized that with ruthenium doping, the structure, there is not much change in structure and there is not much change in magnetic properties, and it is retaining its flexibility as well. Then coming to the important property electrical measurement, because we did all the doping because of changing the conductivity. So this is the device we used for the measurement, and for the temperature dependent resistivity measurement, we saw that the undoped film has a resistivity shown by this, while after doping we can see that there is 3 order of magnitude difference reduction in resistivity. So why this in spinel ferrite, basically the conduction happens by hooping conduction. So in an undoped sample, all the ion exists in Fe3+ state. However, with doping, there is conversion to Fe2+. So there is hooping conduction between these two states. So this is how conduction happens in cobalt ferrite. So after reducing the conductivity by 2 to 3 order of magnitude, we try to understand the conduction mechanism. So we try to fit it with different models. First, we fitted with it with Arrhenius equation shown by this, and we are trying to calculate what is activation energy. So we saw that for cobalt ferrite, we got activation energy of 181 millielectron volt. However, for a ruthenium doped cobalt ferrite, it is decreased to 113 millielectron volt. This is showing that the activation energy is indeed reduced with ruthenium doping. Then we try to fit it with small polar and hooping model, and we try to find this parameter called potential barrier for hooping. Then for undoped sample, we found the potential barrier to be 200 millielectron volt. However, for after doping, it has reduced to 139 millielectron volt. In this case, we are seeing that there is it is not fitted well at low temperature. This is because there is different kind of conduction mechanism at low temperature, which is due to defects in the film. So till now, we saw that there is a change in activation energy with ruthenium doping. We saw that the electrical properties indeed got changed with ruthenium doping while keeping the structural and magnetic properties intact. So the reason for this change in conductance is due to conversion of Fe3+ to Fe2+. So how to prove it? To prove it, we did XPS measurement of Fe2P peak to show that indeed there is a conversion. So we did it for one undoped sample and did it for doped sample. So from this fitting, we could found that there is presence of both Fe3+, Fe2+, and Fe3+. And while calculating the ratio, we found that without doping, there is 16% of Fe2+, while with doping, it has increased to 43%. So this 16% comes because we did the growth in high vacuum condition. That addition to ruthenium doping, high growth condition also helps in conversion of Fe3+ to Fe2+. Then to show that it is indeed only the change of ion valence state and other elements stays intact, we did XPS measurement for cobalt 2p peak, and we saw that it is staying in cobalt 2+ state only. There is no change. However, this cobalt ion is occupying both tetrahedral and octahedral site. Again, we did also XPS measurement for ruthenium, and we saw that ruthenium is staying in ruthenium 4+ state only. So this says that there is only change of ion valence state, that is from Fe3+ to Fe2+ with ruthenium doping. So in a conclusion, we grew epitaxial thin film of cobalt ruthenium ferrite, which is transparent and visible region. And the Raman data shows that there is no change in crystal structure with ruthenium doping, and the magnetic properties retained with bending, and XPS measurement shows that there is indeed change of only Fe3+ to Fe2+. So this is, we are using this material as a channel for making a synaptic transistor for neuromorphic computing, and such flexible devices provide a new platform to develop next generation flexible magnetic device. Thank you.
Thank you, Mona Lisa, for a very nice talk and especially for keeping to the time schedule. I would like to now open up the floor for questions. You may receive some questions directly in your chat box, so please look at that. To the delegates, please pose the questions using the Ask Question link on your screen. There do not appear to be any questions. So with that, let us thank our speaker once again for a very nice talk, and especially the application that she's trying to apply it to, which is a fairly recent and a very interesting area of a lot of work has been done. So we are done with the oral presentations except for one today. Next up is tea break, and unfortunately, we won't be able to join for that because of the coronavirus situation. However, there is a poster session in Hall 3 at 3:30, followed by a invited talk by Professor Guo of University of Michigan at 5 p.m. So please join us for the poster session in Hall 3, while the lecture will be back here in Hall 8. So let us now close this session. Thank you. Okay, hello everybody. Hi Dhiman. So we can begin our poster session. Dhiman, if you're fine with it. So one by one, I think they can present 2 minutes.
Yeah, sure.
Okay, so I think we'll start with, I think so Pushpraj will join us later on because they have another meeting going on. So we'll start with Pushpraj's posters first and then other posters if that's an issue, because he won't make any comments on these posters, and then so do you have the Excel sheet of the posters? I'll send, otherwise I'll to you. Okay, so we can go ahead. I think first we'll say Sushil Kumar, are you there? Sushil Kumar, can you present? Okay, so I'm not sure if the poster presenters are here at all.
And in hall 5, there is another presentation going on at the moment.
No, so right now there are many presentations should be going on. So I think hall 1, 2, 3, 4, 5 all have poster sessions going on. We are hall 5, right?
Yes, but in hall 5, some presentation is going on.
We should be hall number
5.
Yeah, we are hall 5. So is there there shouldn't be anything else going on here? Is it
No,
going?
but if I go through this login, the conference login, it's showing that in hall 5 some invited talk is still going on.
Okay, I'll talk to Professor Khare.
Yeah.
Log into the normal session. Do we have a IT email address that will work? How did you do it?
Using our IIT email ID.
Okay, and password.
Logging.
Okay, so that works. Okay, I think we populated our credentials. In where? Okay, it's gone through.
Yeah, in other halls I can see that the poster is going on, but in our hall some other presentation is still.
Okay.
Depends if you have any query, you can ask to Professor now too. I think someone switched the video. I think one of the participants. So ask questions. I think I forgot who opened the video. I could see the video. Hi, Ekta, do you have any question? No, thanks.
Bhaskar, I think we are in the wrong hall as well because I can see ourselves in the hall 8. So I think this is the meeting window for hall 8. So that is not live right now. Bhaskar, I think we are in the wrong hall as well because I can see ourselves in the hall 8. So I think this is the meeting window for hall 8. So that is not live right now. Bhaskar,
Yeah, hi, Dhiman.
hi, yeah.
Yeah, so the posters are visible on the main website itself under e-posters, and we can probably
Okay.
go through that and then probably ask questions one by one.
So at each poster link, they will be available,
Yeah.
right?
Hello. Hello.
Somebody
Hello.
said, who is this?
Yeah.
Yeah.
Yeah. Sir, I am from backend team,
Okay.
and I think you are in the wrong hall. This is a hall number 8.
Okay, so
Yeah.
this is the link that we had been sent. So I guess he sent the wrong link. That's why. Okay.
Yeah. So
So I'll
can you send the link for hall 5?
सर मैं आपको सेंड नहीं कर पाऊंगा उसका लिंक
okay, I
आपको
think
वही
Dhiman,
जिससे
I'll
आपने लिया
figure.
है वही आपको लिंक देंगे वो
So I have the link for all halls. I'll just send you.
Okay.
So I'll just type it in
थैंक यू
here. You can
Yes.
probably
थैंक यू सर
cut and paste.
Can you see that delegate link? Did you get that? Yeah, yes, sir. Yes, sir. So by going there and
Oh, someone, sorry, I didn't hear. Whole number is 8. Can you hear me talking? Hey, Madhusudan, you hear me? Hey, I couldn't hear any sound. Okay, now I can hear you. Yeah.
Okay, good. Good.
All right.
Okay, it's a little glitchy. It's been a long time.
Right.
In 2013, I think.
Wow, geez. So
It's been 7.
a presiding conference in the comfort of your room, right? That's super nice.
Well, it ceased to be a comfort actually to be a comfort after the first week or so, because working in the office is so much more, convenient. So
Oh, I see. So you don't have any restrictions? I mean, going to work, stuff like that?
we do actually. My lab is currently in quarantine because we found our first case of coronavirus 2 days ago, and so we had to, yeah. So we had to ship in, and it's actually a student in her final year of PhD, so it's come at a bad time for her. So, yeah. So right now we are just getting tested, and next step is to sanitize the lab and then reopen it. And
Sure. I see. So testing, I mean, pretty fast.
yes, it takes 2 days. The first test, and if that's found to be positive, then they go to the RT-PCR, which is
Okay. Yeah.
The PCR test.
Gotcha. Yeah, definitely. Yeah. I mean, the antibody, probably by now, a lot of people have developed some sort of antibody, right? Yeah. I couldn't hear you again. Okay, maybe you're not talking. So we have 4 more minutes, right?
Yeah. So I was just saying, it's probably a better idea to actually have some antibodies, because otherwise you're open to, well, you're still at risk, but the chance of reinfection are lower. So
yes, right.
At least for some time.
Yes.
Can't wait for the vaccine to come, because for me as an experimentalist, it's extremely difficult to run things the way we're already working with reduced staff. So at any given time there can't be more than 4 people in the lab. So how about you? How's Michigan handling it? How's the clean room and all that?
Can shut down the entire school lab, for almost 3 months, and then gradually opened. Yeah. So right now, I mean, we have this maximum occupancy in each room, and overall the on campus, I mean, it's like empty campus even during the So it's they are. I mean, since the school started, the class started, they are increasing number of positive cases. And however, so now everything, the school, the classes are all remote again. In fact, from this week, right? All the kids.
Yeah.
Oh, yeah. I think my internet usually. I mean, I have I've ordered the fastest the internet available. So.
Yeah.
Mm-hmm.
So teaching remotely is not fun at all, actually.
Yeah, no, it's not. Oh, by the way, if there's I mean, internet speed issue, maybe on your side, I can, let me see. Yeah, I'll see. Just let me know if there's a chopping of sound. I can stop the video, maybe, hopefully give
Yeah, I
some
think
little
it
bit.
might be a good idea to stop the video because it was getting a little choppy just now.
Oh, it's all right. Let's try it out. So is it doing better slightly?
Yeah. At least the voice is coming through clear now, at least.
Okay. Oh, excellent. Okay. So maybe I'll just, in the beginning, minute, I'll use videos so that, just to introduce myself and then stop it. Yeah. Okay. You're also attending MRS this year?
No, actually, because first of all, I got roped into this business, so I was going to miss the initial part of it possibly. And second, it's really not the same thing. Boston in winter has its own fun, so why spend the registration fee? I mean, I can use that money for something else.
Absolutely. Yeah.
Yeah. Okay, so I think it's almost time to get started. So let me pull up. All right, so it gives me pleasure to welcome Professor Lingji Guo from Michigan. Jay started his academic career at University of Michigan in 1999 and has been a full professor of electrical engineering and computer science since 2011, with a dual appointment in applied physics, mechanical engineering, macromolecular science, and engineering. He has more than 230 literary journal publications with over 25,000 citations. Professor Guo's research includes hybrid photovoltaics and photodetectors, polymer-based photonic devices and sensor applications, flexible transparent conductors, plasmonics and nanophotonics, nanoimprint-based and roll-to-roll manufacturing technologies. On a personal note, I have known Jay since 1999. I think we both entered Michigan at the same time, me as a grad student and you as a faculty. So it's been a pleasure to know him all these years. So without further ado, I would like Jay to this talk.
Great. Okay. Thank you very much, Madhusudan, for the nice introduction. And today,
one final note: delegates who are not visible in the chat box, So if you have any questions, yeah.
All right. Yeah. So
please start it. Yeah.
Yeah. Good afternoon. Today is Thanksgiving Day in the United States. It's early morning here, and I'd like to give thanks to the organizers and to all of you to tune in to the this talk. Actually, it's been quite some time. I forgot the theme of this session. So when I was asked to provide the abstract, I added the top one, the thin metal film for plasmonic lithography as well, to make a 30 minutes talk. All right, I'm going to start. Madhusudan, I don't know how do I. If you can stop my video from your side.
I think we'll have to ask the administrator to do that.
Okay, you know what? Give me 1 second, because I was told the sound was a little chopping, so I want to get some bandwidth. Let me see if I can. Stop video. Okay.
Yeah, that looks good. Thank you.
Okay. Okay. So the work I'm talking about was done by a lot of students. At least some of the names here. Actually, quite a few have already graduated. Yeah. So the session is about flexible electronics. So looking at the display area, we can see that the display going from rigid to curved display. Now foldable phones are coming to the market, and in the future, people are anticipating rollable displays and so on. Right. For this type of technology, there are a lot of requirements for the materials and devices. Right. Even as simple as the electrode. For the display, we need a transparent electrode, and that has to be flexible. So as a result, the ITO material that dominated for half a century, right, is needing to having a replacement. I believe earlier in this session there was a talk on silver nanowire based, according to the schedule. I couldn't attend because it was in the early morning. So. What we have done in the past, right, over 10 years ago, is that it was published in 2007. We have exploited metal-based transparent conductor. That was in the form of a metal grid, nanogrid. It's what done by nano imprinting. Yeah, And we first applied to OLED. You can imagine that in laboratory, the device is very small, but this MIT Tech Review picked up the topic and gave the title "Big and Bright Flexible Display." I really hope to see that this get into the market in the future. Yeah. Later on, for several years, we published work using this not only for LED but for solar cells and how do you actually in a high throughput manner making these type of structures. As you can see, this is in 2007 paper. You can bend it right without breaking. While ITO, you definitely see the cracks already. This is what it looks like for a laboratory small sample. Okay, and the final the third structure is you can see these nanoscale lines. They are tens of nanometer wide, and so they can resist the bending very nicely. Yeah. Now, that's one way of making metal to be transparent. It's essentially like a window, right? You poke a lot of holes, let light go through. Yeah. Another way is, in fact, inspired by how graphene, is transparent. You try to make materials very, very thin. Okay. And silver. Oh, by the way, in the grid case, you can essentially use any metal. Yeah, it's suitable, compatible with this fabrication technique. Yeah. If you want to make a metal thin and to be transparent, then silver is the best choice because silver has the lowest electrical loss resistance, right? And also lowest optical loss in the visible and near IR region. But one problem with silver is those of you who have tried silver deposition, for example, on oxide, on glass, right? Is that they don't form a continuous film. Rather, they form this island-like 3D, follow the 3D growth, right? Island-like structure. Yeah. This happens to silver, to gold, right? These are all good materials, potentially candidate. Yeah. However, we found a way to solve this problem. As you can see here, yeah, these are all nominally 9 nanometer thick. Yeah. Now we can make it really, really smooth. The trick here is you don't deposit silver on its own. Yeah. And so we can get these ultra thin and sub-nanometer roughness morphology. Okay. So what you do is, in fact, you add another ingredient into it. Okay. We have tried many different materials in a review that's going to come out. We actually list a lot of things that we have tested. Yeah. Here, in this particular example, is using aluminum. So we call it aluminum doping, yeah, because the amount of aluminum is very small, but magically it can spread out the film and make it really, really smooth. Yeah. And once you make it smooth, silver not only can be used as a transparent conductor, it's a very widely used material for plasmonics, right? Yeah. Now, for example, if you try to just simply make these thin metal strips, right, as a plasmonic waveguide, you can increase the plasmonic wave propagation length significantly, as we reported in this work. Now, looking into why it does that, during the material growth, at the initial stage, if you stopped the growth, right, on the left, this is all AFM images. On the left, if you do just pure silver, you can already see these large silver grains. Okay, but if you add tiny amount of aluminum, on the right, you can see that they still nucleate very nicely, but forming much smaller grains and very well distributed. So this trend actually would continue as you get to let's say toward 10 nanometer region. And so as a result, if you look at the TEM of the crystal size, right? On the left, you see these large crystals, the 10, 15, 20, depending on the thickness you grow, right? On the right-hand side, you can see that these grains, crystal size remains about 5 nanometer or even smaller. So this guarantees a smooth surface. Okay. Now, something else that's very interesting for this doped film, pure silver. Again, if you deposit silver in the vacuum and take it out in air, right? Just out of the vacuum, it looks pretty nice, but just 30 minutes after, it actually becomes dark. Okay, just in ambient. But this aluminum doped silver can last for a long time. Yeah, on the bottom left, you can see as deposit. 6 months later, in Michigan weather, right? This did go through the summertime. Yeah, you can see that almost no change. This is quite remarkable. And another thing is that silver, even let's say if you deposit thick enough, they become continuous on the upper left, right? I think this is 15 nanometer, is somewhat continuous. But if you heat it up, adding temperature in 300 degrees C, in even nitrogen, right, it de-wets like water droplets. However, adding this aluminum ingredient, it remains very stable. Yeah, no change at all. Yeah. In fact, we even tested for a short time, like 5 minutes, even 500 degrees, it can stand that. Okay, so it's very interesting, and this is practically very useful, right? Now, again, looking at why it's doing that, we took cross-section TEM picture with collaborating with my colleagues. You can see that these are the metal distribution, atom distribution throughout the film, right? Film thickness is, in this case, the bar is probably 15 nanometer, right? Okay, in B, you can see the silver is distributed continuously throughout the film, okay? And aluminum in C, you can see it's not distributed uniformly, but they tend to have a higher concentration at the bottom interface and at the top air interface. The bottom interface is understandable because aluminum actually have higher affinity, stronger affinity with oxygen, with oxide, right? And there's also a tendency to drive, sort of out diffusion toward this surface. And the aluminum is very reactive, right? They may bond with oxygen and form, we believe, a protection layer. So that helped to stabilize the material. Now, we have also done XPS study coupled with etching test, so you can look at the distribution of different atoms. Yeah, the finding is very similar to the TEM study, so I don't want to repeat it. Yeah, the XPS study was published earlier in 2014. Okay, using the silver, right, as an optical material, especially in, let's say, in the area of plasmonics, the permittivity of the material is of great importance. So that characterizes the real and the imaginary part, epsilon 1, epsilon 2, right? In fact, you can actually tune this epsilon 1 and epsilon 2 by a couple of methods. You can use different doping, right? You try aluminum, titanium, nickel, and so on. All of them can give you a different behavior, okay? And you can also try to do annealing after the deposition. So here you can see that after 500 degree annealing of different materials, yeah, can give rise to different doping. Usually the epsilon 1, it's getting more negative. It's more like an ideal metal. Okay, so this is another knob that could be useful if you want to use this for optical applications. Right. Now, coming back to the main topic, yeah, so we do want to use this as a transparent conductor. Okay, so in this graph A, it shows the transmittance of optical transmittance of the doped silver, right, compared with ITO. Okay, now this just the pure, just the aluminum silver film itself on a glass compared with ITO on a glass. Okay, so ITO as hold on, let me see if I can get the pointer. Oops. Oh, never mind. Okay, is a light green line. Yeah, it's very high transparency. That's why people use it as a transparent conductor. Yeah, the silver itself is not as transparent at this stage. Okay, it's because silver, like any metal, they reflect light, and they reflect more light at longer wavelengths, as you can see. So the lower transmittance is basically due to the reflection effect. But something else I want to draw your attention to is that ITO, right, drops very quickly below 400 nanometer. So for UV, right, ITO is not an ideal transparent conductor. But you can see this silver film, right, down to 300 nanometer, it still transmits a very good amount, right, 70%. Yeah. So this could potentially be used for like UV range LED light, or other optoelectronic devices. Okay, yeah, but this high reflection can be solved. Yeah, if we add materials on top, for instance, in this one shows basically on top of aluminum silver, we add zinc oxide. Zinc oxide is added because, as we know, zinc oxide is very useful transport material for optoelectronics, for organics, right? It can be used as an electron transporting layer for, making OLED or as well as organic photovoltaic. Yeah, that's why we use it. Yeah. And in fact, the earlier work on this was making organic photovoltaic using this kind of a transparent conductor. Okay. Now you can see now the transmittance all of a sudden goes up very high, right? Yeah, well about around 550, right? Green light range is actually well above 90%. This is absolute transparency. Okay. Now we also found that it depends on the oxide surfaces. If you use tantalum oxide, you can get this film as thin as 4 nanometer and it's continuous and smooth. Yeah, so that it's great a fit feature to have. Okay, now talking about in the OPV, in the initial stage, we just this is a very commonly used PV structure. Okay, we just simply replace ITO with our ultra-thin silver film. Okay, everything else, the film thickness doesn't change. Okay, and we found that in the earlier paper that we can actually get enhanced EQE quantum efficiency. That is because silver in here, right? It does act as a reflector at a longer wavelength range. So for organic semiconductor, we know that the absorption gets weaker as it goes towards the absorption edge, right? But by using this reflection, essentially forming a small like Faber pearl cavity, right, on top silver and the bottom thin silver. Yeah, you can show in this upper right figure, right? You can actually enhance the absorption, therefore increase the efficiency. Yeah, we also found that in here, if we add this tantalum oxide underneath the silver, right, of different thickness, you can see in the figure D, changing from 5 nanometer all the way to 50 nanometer, right? This actually have influence on the external quantum efficiency. This may sound strange in the beginning because this dielectric layer is outside the silver, right? It's outside this Faber pearl cavity. So normally it should not have any effect. However, we should notice that this thin silver on the bottom is very transparent, right? So the light can pass through that and it will experience, will see this dielectric. So therefore, one could use this bottom, I call it optical spacer, to tune the resonance, all right? So therefore, you can enhance the absorption and the EQE at certain wavelength range as desired, as shown in D. Okay, yeah. So this E shows the normalized short circuit current out of this device. Yeah, that's just adding another utility by the fact it's transparent and you can actually do things outside the cavity. Okay. Now, this was a more recent work published last year. This is a collaboration with Professor Steve Forrest's group in my department. Yeah, we made a transparent organic photovoltaic cell. This structure is much more complicated. Yeah, and Professor Forrest's group has a very nice infrared absorbing material. So it doesn't absorb very strongly in the visible. Yeah, so we can use that to transmit the visible light and harvesting the light in the near infrared region, right, for photovoltaic current generation. Yeah. I won't go into detail because it actually takes a lot of time to explain, but just roughly you can see that this OPV structure, the active layer, 85 nanometer, right, moly oxide as a whole transporting layer. Anode is where we use thin silver film. Okay. And the bottom zinc oxide, again, is an electron transporting layer, ITO as the cathode. So this is the main sort of solar cell structure. But in order to get the desired optical effect, namely high transmittance in the visible, yeah, we have to do a lot of other tricks. For instance, on the bottom, we add anti-reflectant coating layer to let light go through the glass interface easily, right? And this outcoupling layer, this yellow blue, the yellow color, consists of a stack of two materials. Okay, this is meant to again output the visible light and reflecting the near infrared. Okay, so therefore we can actually recycle the near infrared light for stronger absorption. And DBR mirror on the top is for the same purpose. It's mainly to reflect the near infrared light. Okay, so by doing this, we can actually get pretty decent quantum efficiency, right? And this so-called LUE, I think it's called light utilization efficiency. Yeah. And you can see it on this picture, right, on the bottom part. That's the OPV. Yeah, it's actually, you can by using this optocoupling layer to tune this cavity, you can actually make it colored, slightly colored, or you can make it neutral. Yeah, on this picture it shows sort of the neutral PV. So this sort of device, you can imagine you can actually use it to make windows, right? That light transmits through, but you can actually generate useful electricity. Now, we also apply this material for organic light emitting devices. Yeah, so you can see here, this is a polymer OLED. You can where we just replace the ITO with our thin silver. Okay, and where we can see the current efficiency or the external quantum efficiency of this device enhances as compared with ITO. Yeah, everything else, the layer 6 structure is the same. Yeah, but you can see this enhancement. Okay, so why is that? All right. By the way, the top one shows the curved, right? And recently, this is this result described in this paper is using a polymer. It's a super yellow polymer semiconductor. But we have now made a small molecule based and with much higher efficiency and so on. I couldn't actually present here because it will be presented next month in IEDM. They don't allow any previous public disclosure. So I just show you a picture of green emitting and a nice looking curved device. Yeah. So the reason for that is that in OLED, right, it's a common knowledge that, I mean, even you get internal quantum efficiency to be 100%, but light simply doesn't come out, right? It can be guided, especially when you use ITO, right? And also can be internally reflected at the glass-air interface. The only small amount of light, 20 to 25%, gets into the air. But previously, people have to use very complicated structures, gratings and corrugated structures in order to couple the light out. And those are, they're not compatible really with mass production, as well as it can actually be intrusive to the OLED structure. Yeah. So we think our strategy is to simply replace the ITO with a thin metal film, right? To suppress the guided mode is a much practical approach. Yeah. And this result will make out to the public soon. All right. Now, just one slide to show that because as I said, the thin silver, right, is actually very reflecting at the near infrared. It's even more reflecting if you go toward longer wavelengths to the for the RF regime, right? It's going to be a perfect reflector. So in that case, you can actually make a transparent electromagnetic shielding, right? A blocked RF field. Yeah. So we have published a couple of papers, and I won't delve too much. Yeah. By adding a thin graphene layer as an absorber, you can actually make it an absorption type of EM shielding structure. Okay, now let me use the last few minutes to, I see, okay, yeah. Here's another interesting work we published this year. So we know that metal is has loss, right, as reflecting. So if you deposit onto a surface, we expect the transmittance typically gets lower, right? But we found that, let's say if you take a PET plastic substrate, right? Now, if you design these structures correctly, right, really look into the math and physics, right, you can actually get a result very fascinating and counterintuitive. You can actually, after depositing this layer stack, right, you can get overall transmittance higher than the PET itself. Yeah, this may sound strange, but I can explain it using one slide to discuss this sort of possible, right? This one case is a 10 nanometer silver. You can calculate, the transmittance and reflection. The transmittance is dashed black curve, and the reflection is very high. This solid black curve, right? But just adding the zinc oxide 40 nanometer on top and bottom, all of a sudden, right, you can drop the reflection to the bottom curve, and transmittance goes up very high. Okay, yeah. So what happens is 40 nanometer zinc oxide acts as an anti-reflection, simply anti-reflection coating that's often used in many optical systems, right? You can achieve this. Now, if you add a 40 nanometer, change this upper stack slightly, adding aluminum oxide, which has a lower index, right, than zinc oxide, you can actually reduce the reflection even further. So because you created on top this graded index structure, yeah. So that's why we can actually achieve that seemingly impossible result. Okay. And here shows a large sheet that was deposited by row-to-row co-sputtering process. My student holding this large piece. Yeah. Now, tune into last few minutes. Just briefly talk about other use of thin silver. Right. Thin silver has been used in this 2005 paper in the Science paper, the super lens to get high resolution imaging. Yeah. And and later on, their work on, again, using silver or stack of silver to create these very impressive results. Using 365 nanometer, you can get down to like 50, 60, 70 nanometer lines. Yeah. But the problem is that it's very shallow, okay, and it's not uniform even in this tiny area. Okay. Yeah. And this is because this is in the concept of plasmonic lithography, right? So we know if you want to focus a light, right, it's always limited by the diffraction limit. Okay, so you can try to reduce the lambda. In plasmonic, the surface is a surface plasmonic wave, right? The wavelengths can be much smaller. So in principle, you can actually solve this problem. Now, this earlier work, right? The reason that it's shallow because we know the surface wave are evanescent wave. So they decay very quickly in photoresist that they want to expose. Okay, and also the silver is it actually transmits a quite broad range of K vectors. Okay, that's why it can resolve very small features. But we know that this, in fact, if you think about interference, right? If you have a first order, plus minus order, they can interfere in nice sinusoidal wave. But if you actually introduce higher order, it gets distorted, right? So we think that's why even in small area, you get non-uniformity. So we set out to solve both these problems, okay? So what we did, we tried to, we want to get sub-wavelengths and very high aspect ratio and be able to pattern large areas with good uniformity, okay? So here the structure is kind of similar, right? Except that we actually use aluminum now to replace silver, and we can now use a very thick photoresist, something from 100 to 300 nanometer, yeah. And we want to actually get a uniform exposure and getting the result, yeah. And the aluminum here is the purpose is actually it's using as a spatial light filter. It only passed the order that we want, diffraction order. In this case, plus minus 1. Yeah, this simulation result, you can see that throughout the photoresist, right, this light intensity distribution is very uniform, right, rather than evanescent, because we're actually using it as a waveguide. There's a waveguide coupling effect. Yeah. Looking at the result, right, so we use 4 or 5 nanometer as a sort of a blue light. Yeah. And we can get down to 55 nanometer lines. That's 1/6 of wavelengths. Okay, and you can get a very good aspect ratio, 1:2. Right. We can also get even higher aspect ratio, but those lines collapse because they're so tall during the development. Yeah. One last piece is that you can rather than using just one layer of silver, you can make metal. You can make the stacks. Dielectric metal. In this case, we'll use aluminum stack, right? It's form a so-called hyperbolic metamaterial. Yeah, and you can tune the thickness and so on. You can make it absolute near zero. Yeah, the permittivity close to zero. Yeah, under such condition, you have a very interesting feature that now we can use a mask that's much bigger, like in this case, 700 nanometer period. All right, but we'll still be able to resolve things, okay, the half pitch is 58, right? So the mask period is 700, but now you get like 110, right? So there's a reduction. This is similar to in projection lithography, right? You have a 5x or 4x reduction. So now you can use a larger mask, but be able to resolve much smaller features. Yeah. So we can now further extend this to sort of roll-to-roll process, which my lab has done a lot of work in that area. So just to use one slide to summarize the transparent conductor business, right? So we can, if we compare ITO, metal mesh, silver nanowire, right? The silver, thin silver base, in many aspects, it stands out. Very low resistance, high transparency, almost no haze because this is continuous film, and very good flexibility, right? And the manufacturing side is very simple. You can actually use a industrial sputtering process and do roll to roll. Yeah. Oh, I should mention that this is licensed to a startup company that I co-founded. It's called Zenith Nano. It's now commercializing this transparent conductor for applications, for example, in touch panels and others. Okay, I think I've used up all my time. I will stop now. I don't know if I have time for a question. Thank you again for your attention.
Thanks, Jay, for a very, very nice talk. I think we learned a lot about this, especially plasmonic nanolithography, which I had looked at like 3-4 years ago and then dismissed it as because I did not have the right facilities for it. Let us open the floor for questions. The audience, please use the Ask the Question link on your delegate screen, and then it should appear in your chat window.
I couldn't find the chat box. Oh, here. Okay.
So I have a question of my own.
Sure.
During
yeah.
So during the growth of this very thin silver layer that you're growing for the transparent conductor, what kind of growth rate do you target? If it so, because that affects the kind of coverage you're going to get. That's the aluminum silver composite that you're forming.
Yeah, it's a little chopping up. Did you ask the substrate material, or it was not very clear? Can you say it again?
No, in the co-sputtered growth of silver and aluminum that you're doing,
yes.
what is the typical growth rate that you're targeting?
Oh, growth rate. We in our lab we actually deposit slowly, but in company, right, when they actually do roll to roll deposition, the speed is fairly. Yeah, I don't some of these industrial level operation, I don't know the details. Yeah, it can be pretty fast. I mean, because practically for the throughput directly links to the production cost, right? So in order to reduce to a reasonable cost, you actually have to ensure certain throughput.
Okay.
Yeah, and the film, the other thing is compared to ITO, right? Here you only need a few nanometer. You get the resistance. By the way, I don't know if you can still see this slide, right? The resistance is naturally very low, right? It's typically well below 20. Yeah. So ITO you have to get really thick, right? That would require a lot of deposition time. Yeah.
Any audience?
We wouldn't know how many people are actually tuning in, right?
If I ask the host, they can tell me, but this is being relayed, so
yeah, no need. Yeah. Okay, I guess it's probably pretty late in your time. I mean, people may have a more rest.
So no, it's not actually that late. It's 5:30. So I guess people rushed off to a cup of tea or something like that. So
Correct, yeah.
anyhow, so there are no questions received so far. So I would like to thank you again. Rising this early on Thanksgiving Day itself is something that used to be completely verboten back in the day, but these days, because one day seems just like the next because of thanks to coronavirus,
That's right.
that distinction is kind of broken down. So
It is.
have a great Thanksgiving. Sorry to rouse you on so early. And I would
No.
like to again thank you for coming and delivering a very nice talk that I think we learned a lot from. So thank you.
Okay, it's my pleasure. Yeah, thank you very much. Okay, take care.
You too. So this actually ends our business for the day. We will reconvene tomorrow at 5:30 in the evening with the first of the 3 invited talks that are scheduled for tomorrow. So I would like to thank all of you who are in the audience who have patiently sat through the various technical issues that we faced during the day, and for making a lively audience removed from brick and mortar realities as it is. So thanks once again, and have a great evening or morning, depending upon where you are in the world. So thanks. We will see you tomorrow. And one thing, it'll be in Hall 4, not in Hall 8. So we'll be in Hall 4 tomorrow.
Hello, hello, hello. Yeah, Mr. James, you are not audible. I can't hear you. I can't hear you.
Can you hear me now?
Yeah, yeah.
Sorry.
Yeah, what's your hall number?
Somehow I have a big echo here.
Your voice not clear.
Yeah, but let me use the chat because I have a very annoying echo in here. Hello, have you seen my chat message?
Can you hear me?
Hello?
Yeah.
Yeah, hi sir. Can you let me know the what is the topic of your sessions?
I think it was biomems,
Biomems.
or let me. See, the documents don't really have the session name.
Okay. Documents.
Yeah, the web links. Like I have a couple of web links, but let me just.
Sir, it's very difficult to find how to do. There is there is 8 sessions hall running right now, and in that 7 hall is almost completed for the day. Only hall 1 is working now. If you want to need that link, I will share with you. Hall 1.
Yeah, I don't know. I never had any hall numbers. I just had
Okay.
links here to the Cisco that I
Okay.
clicked on this morning.
Okay.
Can you see my screen?
Yes, yes, I can see.
So I clicked on this screen, this link here, right?
Okay.
So that was the reminder I received this morning.
Okay.
And that led me to the wrong session.
Okay.
So this is the agenda that was, if I share it with you.
Yeah, yes. Can you click on that, sir? Agenda. Okay. Okay. It's a right link and the right hole, but it's a for tomorrow.
So that was for the 26th.
Yeah, yeah, but in as per IST time and date, I mean Indian Standard Time and date, it's a session, your session on tomorrow at 1:30 to 2 p.m. at IST time.
Yeah, but that, I had some communication. Let me see.
You are from joining at which country, sir?
Just 1 second. See, this was the last message I received, and that's what my schedule.
Yes, yes, and it's on the two, day two, and the session invited lecture 4 after the lunch break.
Okay, but why did I get the message today, this morning, here, this message?
Maybe it's due to country, maybe due to
Okay,
maybe due to time zone.
so this is for tomorrow.
Yes, this is for tomorrow. After post lunch, it's 1:30 to 2 p.m. It's a half an hour session.
That must have been shifted again because, I'm in Ireland. So 1:30 is very early for me. So would my talk be at 5 p.m. or Indian time?
No, it's as per Indian time is 1:30 p.m. 1:30 p.m. as per Indian time.
That's a session, right? That's from 1:30 to 5 p.m. But at what time in the session would I be up?
No, it's your session time, sir. It's a 1:30 to 2 p.m. as per Indian Standard Time.
Yeah, but that was agreed differently because that puts me quite early in the morning,
Are you from Ireland? Right.
Yeah, I mean, I that was the original time slot, and then the organizer shifted it to 5:30 p.m. Indian time. So it was more convenient for me, and because I have things scheduled early in the morning.
Okay. Let me check the updated agenda. Let me check. Just a second. Let me check. I will get back to you. I am audible. Let me check, and I will get back to you.
Through email?
No, through here only. Just give me 2 seconds, please.
Yeah. Thank you.
Okay.